Hello everyone. Does online right now the Zoom users can hear me?
Yes, I hear you fine.
Okay, great. Can you see my screen right now? The presentation screen.
Now I see your face.
That's okay. So share screen. Forgot that.
Now we see your desktop.
Yeah. What about right now?
Now I see your slides with title screen.
Okay, that's great. Yeah. Okay. Welcome everyone, and welcome to the 6th International Workshop on Visual Dormitory and Computer Vision application based on location clues. My name is Guoyu Lu. I'm an assistant professor from University of Georgia. And there are some other organizers, Yan here from Illinois Institute of Technology, and the other three organizers, British Frandolfer from Graz University of Technology, Niku Sede from University of Toronto, Chandler Kampantu from University of Delaware. They are not here. They are not in person in CVPR this year, but I would like to thank them to helping to organize this workshop. So first, briefly talk about why we want to have visual dormitory and location-based clues. There are multiple different reasons. For example, robotics, you want to navigate your robotics, and you want to find the correct place and go to the correct place and find the pathway to avoid obstacles. And there are some other applications like augmented reality. You want to project the exact graphics on the correct position and is the correct angle, right? And also we want to estimate the odometry information, and so that we know what is the motion of my robotics or vehicle or camera. And at the same time, we can build a map, and which the map can be used for many other applications, for example, navigation and also visual dormitory. One of the output is also depth and range estimation. And from the depth and the range estimation, we can really estimate what are the object distance from my camera, from myself. Okay, and also quite a lot right now, if you go to use your iPhone or Android phones, and you will frequently receive those kind of messages, ask you whether they allow you to use your location. Okay, they want to use your location to give the labels of the images, to understand what is the location and provide services based on location. So that is important to know the location information, and using the location information to provide quite a lot of services as well. And also in many other applications, like in agriculture, and the people want to use agriculture, use visual dormitory location to build the maps for the crop field and to estimate the crop field. Many other applications like medical imaging, and they need to navigate the robotics arm to do the surgery. And in the civil engineering, which later Dr. Aliga will give us more about his research, and also mobile computing. Okay, so this is the basic motivation. Also in our program is starting from 12:45 until 6:30, and we are several minutes delayed, and I think we should be fine. And at the same time of the in-person audience, we will have also online version, which is actually live stream to YouTube, and everybody feel free to ask questions on YouTube channel, and I will read the questions on behalf of the audience. Okay, and we have in this session, we have 7 world-renowned invited speakers from both universities and industries. And the first one is Dr. Daniel Aliga, and from Purdue University, Dr. David Crandell, and from Indiana University, Dr. Xinyu Du, and Dr. Yao Hu from GM, and Dr. Enrique Du from Stephens, and Dr. Yanxi Liu from Penn State, and Dr. Mahit Gupta from University of Wisconsin Medicine. Okay, and also we have 5 executive papers of the very strict peer review process, and they are from universities and the industry as well. So this is the first session. We will have 2 keynote speakers, 4 keynote speakers and 3 talks, and the Dr. Xinyu Du and Dr. Yao Hu will give a combined talk and representing GM. And later we will have a paper presentation from the same group as well. And after a short coffee break, we will have the second session, which involves more heavier presentation, and which has 3 keynote speakers and another 4 paper presentations. Okay, so the first speaker is Dr. Daniel Aliga from Purdue University, and I want to briefly introduce him, and it's very great pleasure to have him to introduce his research. And Dr. Daniel Aliga is currently a full associate professor from Purdue University, and he received his BS from Brown University and MS PhD, and from University of North Carolina. And he's associate editor for IEEE TVCG and also for the Visual Computing Journal. He has been committee members for many prestigious conferences such as CGRAPH, CVPR, ICCV, Eurographics, AAAI, and he has received a Fulbright Scholarship, Fulbright Scholar Award, and the Discover Park Faculty Research Fellowship, and his students also received many awards from Purdue. And he's also a member of ACM CGRAPH and ACM CGRAPH Peer Pioneers, and he has been a chair for multiple committees and in the College of Purdue as well. And he has received about $40 million grant. That is a lot, actually. And as a faculty member, I know that is a lot, 40 million, actually. The 19 of them are actually as PI. And all the funding results from NSF, from USDA, from Google, Microsoft, many different companies, and he's heavily involved in the modeling for urban scenes and architecture and many other areas. Okay, now it's time for the first presentation. Dr. Aliga, you can go ahead.
Sure, thank you. I guess if I could share my screen.
Yeah,
right?
let me stop sharing mine and you can try then.
You're still sharing your screen.
I'm still sharing. Okay, let me just stop sharing now.
And you have to enable that I can share it too, it says here.
I don't know why it seems like I couldn't find the stop sharing button this time. Oh, it's actually the Zoom button is on this screen. No. I couldn't see.
That seems better.
You still cannot see, I think.
I can no sharing, but I cannot share my screen. It says you must enable participant screen sharing.
Yeah.
So why?
I think I should be able to right now. Can you try right now?
Yes, there we go. There, can you see my screen?
Not yet. Can wait a minute. I need to share. Well, it's strange right now. I can see your screen. The audience cannot right now. I think right now everything should be fine.
All right, so screen is good.
Yeah.
All right, great. So thank you everybody for attending. Sorry I couldn't make it in person, but the world is too big and I couldn't make it there in time. So this is a project mostly about modeling places that are difficult to model with a focus on urban environments. So maybe for localization or as a prerequisite for localization, for many applications, we need to know information about the urban location. And then if we have that, we can do a variety of what-if urban tools. So that's the broad scope of the research we've been doing, and I'll be talking about here. And this is important for a variety of desires, such as, for instance, there is a occurrence of natural hazards, and that causes urban damage. So we want to be able to predict and mitigate perhaps what we can of natural hazards. Flooding, lightning, hail. There's also a rampant urbanization across the world. So cities are growing in some places at a very crazy rate. So we also want to be able to deal with this rampant urbanization. There's also congestion, so traffic and carbon dioxide production and other things, and smog and waste, other things in the urban environment we want to be able to deal with. Furthermore, there is needs to be some balance between urban forests and the urbanization process, that we have to manage these two worlds. So from my point of view, we want to use graphics and vision to understand these complex interdependencies between the urban form, function, and the natural environment. This is obviously a multi and many disciplinary adventure. So although I'm in computer science, I've been collaborating with people in many fields, as you can see here, in a variety of projects, trying to improve this interface between 3D modeling and these applications. It's funded by a bunch of people. And of course, I'm talking here today, but I've been working with many collaborators and graduate students, both graduate and undergraduate, over the years. And of course, they are the workhorses behind this. And here are some of their names. So the challenge is we want to obtain what's called an urban form, and the word often is called the urban morphology, so we can do urban planning and mitigation of large complex cities. And unfortunately, obtaining full and complete models of towns, cities, so forth is hard. And in fact, even if we don't focus on the large cities, but in the smaller cities, it's still difficult. And we might want to focus on the smaller cities because that's in fact where most of the people live. So here in the US, right, you can see of the 19,000 incorporated urban locations, most of them, or 16,000 of the 19,000, have a population of 10,000 or less. So most urban places are small. In Europe, it's the same thing. Here's another graph, and basically it says a similar story. So it means that 80% of people living in cities are not in the big cities like New York, Paris, Beijing. They're in fact in small locations. So while sometimes large cities are very well studied and are data rich, that's great, but most people are not living in those large cities. So then that leaves us with a problem, which is that we cannot assume that we've captured all these small cities, because often these small cities don't even have the resources to do the modeling. You might have heard of many projects modeling New York City, Chicago, Paris, and so forth, but the small cities are not often receiving funding. And despite that, therefore, which means that we have very partial information about these cities. So often the questions we need to answer is like, if we have only sparse, disorganized data, how can we organize this geometric information? If all we have is a small piece and maybe with a lot of occlusion, how can we get the full detailed structure? And more particularly, if it's low detail and blurry, how can we get it? Or what happens if we only have 2% of a city modeled? How can we obtain the full 100% of the structure? These are types of questions we want to address. So just to give you some pictorial examples before going into some detail, which I have in my limited time. For instance, here is some aerial data from satellite, latest Planet Lab satellite, which captures the world daily. But this is what you get. So I can ask you, where are the buildings? It's hard to extract from this level of satellite data. variety of current deep learning methods give you some sort of resolving power, but we've been developing things, something like on the right here, where we don't just exactly do segmentation, but we actually are going to generate through deep generation, through deep learning and knowledge of how a city works, some detail of this urban location here. So on the left here is a satellite, and way on the right is our output, and this is ground truth. So it's not exactly the same as ground truth, but much more detailed than the other methods, because again, we're not just doing segmentation, we're actually understanding how cities work, and we're generating a plausible city reality. So I'll give you some more details later. Here's another one with trees, right? So I can ask you where are the trees here, and they're very hard to see. But again, through some mechanism we've been developing of understanding trees or urban trees, we're able to infer the location of trees to relatively high accuracies, as you can see here. This is active current work. In fact, we have a paper this year, CVPR, which relates to this. I encourage you to go there and learn more about our tree work. At another level, we have, for instance, worldview or satellites. This is the highest resolution satellite around. That's a 0.3 meters per pixel. And if we look at imagery that we get and we somehow paste it on a proxy of the geometry, we have issues like low resolution, trees on top, and so forth. So we have developed methods where you go from this kind of left type of input to things like on the right, where we're able to kind of infer the pattern and the structure underneath here, and even look behind the trees and obtain things like here on the right automatically. Same thing here in the bottom. Gives us a much more precise modeling information. Other work that we've done. Also, we've been working in some one-shot techniques, so single image reconstruction. So if we have so the previous two were satellite imagery. This here is a ground level imagery, and it also works for aerial level imagery, so UAVs or planes. From a single picture, we infer the whole 3D structure to within some plausible accuracy. So again, this is working on this notion of we can't sample everything, we can only sample a subset of things. All right, so with that kind of brief introduction, that's a sample of research methods we've been working on. I don't have time to talk about all of these things, but we've been working in things that deal with satellite, aerial ground imagery, and also LiDAR and other scanning methods. And we'll be mostly focusing on things in the city and building scale, but we have in fact worked in all of these categories. I'm just going to talk about some work for now at the buildings and later at the city scale. So in buildings, again, the imagery could be satellite, could be ground aerial, or could be geometry like through LiDAR. And the problems that exist is the following. The satellite scale, even the best around, it could be that the whole facade, the side of a building, is only 20 pixels. So how can you get full detail from 20 pixels? That's the question. If you talk about aerial and ground imagery, your resolution is probably higher, but it's more difficult to assume you've captured every surface because you have many surfaces to see and you can't fly everywhere. You go to like a scan and you'll be missing surfaces. There's also occlusion. So even though you can see all sides of buildings, they might be occluded by other buildings or by trees and other structures. Then if we have geometry, the complications is that it's often unstructured, messy, noisy, things like that. So these are the problems we tackle in these three categories. To give you some idea of things that we've been doing, in this first work, which is several papers, we've been reconstructing the size of buildings from satellite imagery. So this is actually what the size of buildings look like from the best satellite around once it's been geo-registered or also rectified the best possible. This is what you get. So, using other methods, right? It's hard to necessarily complete these facades, but we've been trying to do methods to obtain better quality results of these facades in terms of detail and resolution. So this is the one method that we're excited about. It has a whole pipeline, but it has deep learning, optimization, a bunch of methods that I can't really describe in detail right now. But the inspiration is that we know that there is some sort of rules behind how facades are created. So here's just a subset of possible facade organizations that we support. Each one of them is really parameterized, and it's a whole family of possible facades that exist, in kind of sense can exist. So using those, and also the idea of we only see a small fragment of a facade, or a small piece here, and if somewhere there's a small piece of a building that we can see well, then we can replicate more of that. Like in this case here, this side we can somewhat see well, this side we cannot. Same thing with some of those examples here. So then we can piece together this facade and synthesize and grow the whole face, all faces of the building. So this is the example you saw very quickly before. So this is the actual satellite imagery, best as possible. And by the small pieces we can see here and there in the satellite, we can infer the pattern and then complete the whole, all the faces of the building, as you can see here. And this is done automatically and very quickly. In this same work, we also worked with reconstructing the geometry. This is part of a larger project. So we had these complex buildings that were created by processing satellite data with multi-view satellite data. And then we had some additional component here that actually created 3D models from these multi-view satellite imagery, and it worked reasonably well. These are some particularly difficult buildings here to create. As you can imagine, this is actually Prudential insurance building. There's a real building that's not your typical boxy building. It's a little more complicated. So this is some other geometry work that we did as part of this. And here's another one. And then we can put this together. So we put the geometry and the imagery or facade resolving details together, and we're able to create things like what you see here, which are quite similar to Google Earth, which is aerial data in this case. So this is for comparison. So this is we obtain using satellite data and automated geometry processing and image processing. We compare this to Google Earth, which is quasi-automatic, but of course it's using aerial data, not satellite data. So it's a different data source. Now, this is what I mentioned about given an image of a single building, what we can do. So here you select the building. You select the building, and then through a deep learning process, just from this fragment that you select, it will infer all the way around the full structure. And the structure is not going to be necessarily identical to reality, but it'll be pretty close. So we've done this both with ground level as well as aerial level imagery. The process here is multiple stages. There's a building mass estimation, so automatically estimating 3D camera parameters as well as building mass parameters from this single image. Then for each facade, we do a facade level processing that maps it to some regularized facade. And then the facade, we individually look at each window, and then there's a window stage process, and finally we output a 3D model in whatever 3D format you like, and then that's the final output. I forgot to say, if there are any questions, I'm not sure what the format is, but yell out or something, or I can answer them later. And then so that we use some CNNs, we have a set of a kind of a large space of possible masses buildings can be, and then facade stage, some further deep learnings, and also a potential family of facade grammars that all facades can belong to. And then similarly for windows, we have a large family of parameterized windows that windows and doors can belong to. And the output is what I mentioned here. I think this is a series of buildings to show you, at least pictorially, some of the outputs. And we got images from ImageNet and from sons of various data sets. We just typed in the word building and got some images out, and we just processed about 100 of those. Of course, the building doesn't have to be existing, and also we could do multiple buildings. Of course, we can do kind of a whole street front just by selecting each building and inferring it automatically. And these are the aerial results of aerial imagery. It's a little more difficult to get the precise camera parameters from an aerial image, but it still works reasonably well. We also deploy this to a tool online. So you just upload your picture, you press a button, and we developed this server client interface. It went off to some computer. It was actually in cloud Google services or Google Compute services, and it inferred your building, gave it back. And, we did estimations like it took an average a few seconds, cost 65 cents to reconstruct the building and so forth. And of course, it doesn't have to be a building. We could also sketch stuff. So derivative work was we could sketch buildings. And as you sketch, it kind of automatically infers the rest of the building. So you only sketch a small piece and the rest of it just kind of pops out. And really, this is window here. It's not shown of the possible completions, and you select which completion you want, or you just automatically let it give you the most likely completion. So this is, of course, sketching of urban structures as well. Okay, and the third group is buildings from unstructured geometry. So here is the case that we have some kind of triangle soup or mesh soup of a building, and from this we automatically infer kind of a structured organized program, procedural model of this triangle soup. So this is a very simple building, but it infers this text here. And once we have this text grammar-based 3D model representation, we can, of course, do simple changes and create different buildings and more buildings and so forth. We apply this. So this is actually solving a NP-complete problem with some algorithmic and heuristics. So it's able to take in reasonable time. It takes from minutes to maybe like half an hour to reconstruct, to obtain the hierarchical model from any polygon soup. We've done this with, these are just obtained by architects. They create this in disorganized fashion. We also process scan buildings, lighter outputs, and so forth. And here's some explanation. I'm going to skip over that. So once we automatically create a 3D model for this, we can then use your favorite modeling program. It's nicely organized to edit the building in any way. This all just takes a few minutes because now it's a fully structured hierarchical model. When we just started with polygon soup or mesh soup or scan soup. Okay, taking my time. So now let me jump over to city scale. So city, of course, is a much larger structure, very dense and complex. So we want to create something which is statistically similar to this city based on satellite products. So one interesting project we did was we used land scan. So this is actually a world product that obtains for each square kilometer roughly how many people live in the world. And then we use some global elevation data, which is not very precise, but it's a sample, a 30-meter sample. And we use some kind of satellite data that's been segmented to select which areas we want to create. We plug this together with our, again, procedural inference system, which has a bunch of components, and we have a bunch of papers developed over time. And we estimate from the satellite data, we estimate parcels. So parcel means the segment of land surrounding each building, which there is no physical barrier of that, but we infer this. And from each parcel, we then infer here are the parcels. We infer plausible structures, buildings, using population data and elevation data. So think of it as given a parcel of land and people and a building type and streets and there's a most likely structure. That's what we infer. So we have a calibration process for some city where we assume we know roughly 5% of known building area. So we know the area and count of buildings for about 5% of the city, and then we get in, and the plausible inference we create is accurate to within an average of like 5% error. You can see here the red is the best numbers we get. It's 5 to 7% error on average. We've done this for about 20 cities in the world so far. So this is some idea pictorially. The right here is actually Google Earth and a close-up. And this here is just shown in a similar way, our 3D model rendered in a similar way to make it a plausible comparison. So this here is hypothesized by our system, and this here is the actual reality. And again, several cities, New Orleans, Dublin, and here's a little video zooming over our synthetic recreation of Chicago that's hypothesized from population, height, and building classification data. And here's some other ones, Toulouse. San Francisco, and a few more. And we've done other work in the past for fully synthetic environments, but I'm not going to really talk about that. Okay. I think I'm at about 10 minutes left, so let me switch now to some applications. So what do we do with this, right? So what can we do if we're able to quickly infer buildings and cities from very small amount of information? So we can't do anything we want because, for instance, if our purpose is real estate and showing you the exact building with the exact number of windows and counts of bricks, that's not what we're able to create because we can't create a brick by brick accurate reconstruction. But it is accurate in urban morphology for a variety of interesting applications, which is what we've been working on. So we have several collaborations and in several areas and several cyber infrastructure we've created over the years, and I'll talk about these in some detail. So first is about cloud control. So maybe a little background is that the urban form and material, so the shape and albedos of a city actually affects the local weather. It doesn't mean that you can design a city to be summer when it's like in the middle of Alaska winter. No, you can't make that, but you can modulate the city's temperature by a few degrees on average Celsius, which is quite significant. Some cities have recorded, studies have reported about 8 degrees variation based on the local city design. So it can have an impact. There is some question of whether the current city designs, maybe if not done correctly, can increase the possibility of there being tornadoes or hails or strong events occurring over the city. So these are things that are currently actively being studied by my collaborators in the fields of urban atmospheric science, for example. So this is some work about cloud control. So can we alter the albedo and shape of a city to alter the cloud formation? Now, it might not be that we can make it be a city always sunny that's never cloudy, because there could be an external phenomena that's strong enough that we can't avoid clouds. But in some conditions, we might be able to alter the shape of the city so as to there be no clouds at 1 p.m., no clouds in the morning, or no clouds in the evening, for instance. So this is a tool that we created for this purpose. Another one we might have heard of is the urban heat island. These cities are hot. They radiate, they absorb heat during the day, and they irradiate it during the night. So can we modulate the temperature? So by adding white roofs and parks in a city, we can in fact modulate the local temperature. So this is something we're able to do. So our models that we obtain are sufficiently accurate to use in these simulations. So therefore, we can tell us, gee, what roofs should we model? Should we make white? And that will reduce our temperature by a few degrees centigrade on average. Here is one with urban greening. So this was, in Indianapolis. So again, we created a model of Indianapolis using our system. It was fairly accurate. And then we can, we can play God, I guess, and green the whole corner of the city. But we're not just making this green. In fact, what we did is we made this green, and whatever people and jobs were here were actually displaced to here. So this Indianapolis here actually has more jobs and people than what it did initially when this was not green. So this is a plausible change of Indianapolis. And some configuration might make a big temperature change, like here. This greening actually increased city temperature. This greening overall reduced it by a few degrees, 2 degrees. So, while we can't necessarily do such large greening differences, right? We're not going to destroy 30% of the city and redo all of this. We can do things like plan urban policies about where should there be greening, circular greening, some kind of park distribution frequency. This might be of interest to growing cities to know how is it best for them to distribute their parks to yield some desired temperature phenomena, temperature behavior. Flooding is another application we looked into. So, flooding is an issue in some cities. And while there is what is called active flooding prevention. So you make big canals and walls or dikes, and you redirect the heavy river water or the sudden flash storm water course, you can do that. That's also believed to be a bit disruptive to the current city. There's also a current tendency, particularly with people together in Northern Europe, in Belgium, there is what's thought of as passive flooding prevention. So can we alter the urban design so that it's less prone to cause flooding? Rather than building big walls and canals, how do we change the philosophy of creating cities? So in this work, together with some simulations, porosity-based hydraulic model of how water would go through a city if there was sudden flash flooding, we're able to correlate how changing different aspects of an urban design would affect the weather. So again, by using our urban modeling tool, we recreated 4 or 5 big cities in Europe and the US that this group was studying. And then we're able, since we have at the output a synthetic model, a parameterized 3D model, we can then play with design parameters and then run the simulation again and determine which parameters seem to influence most urban flooding and therefore enable us to passively mitigate urban flooding. So this was the most dominant parameter. It was 9, which is building coverage, and these are a little more secondary parameters. We also deal with urban traffic. So again, as you know, traffic is an issue in cities. So, how can we alter where people live, where people work, so as to reduce travel time and carbon monoxide? So we came up with different scenes, different scenarios. How do we change the direction of roads plus move jobs and people around to reduce traffic? So this is also something we're able to do with the models we're able to infer. Okay, jumping, I have about 4 minutes according to my schedule. We've made several cyber infrastructures, which are these tools that people can use to then, for their city, recreate their 3D models and run some subset of these tools that I've mentioned. One of them is called UQ, which we're still working with. Lego, this was financed by IARPA, so this is the kind of the intelligence agency in the US, the research part of it, and here we're trying to recreate models of any city from satellite automatically. So this was a competitive program. It was successful from our point of view, and this is currently under transition somewhere in the intelligence world. Another project together with Berkeley was deployed in San Francisco area. It affected about 7 million people. The urban planning there department had 7 million people that they were dealing with, about over 1 million parcels or buildings and houses. So we made some software to help their urban planning along the lines of what I've talked about. Wood Up is a grassroots organization. You can Google this. Here's the address. And we made some of the initial tools of this, but now it's grown and more people are contributing with tools, and it's useful for creating weather, air quality, and many other urban planning applications. This is another deployment of ours in collaboration with other people. And then finally, now we're dealing with urban forests. We have at least one. We actually have another funded forest project. We're trying to develop forestry tools to help with urban planning in the cities and also away from the cities. This project is actually going away from the cities, and we have other projects going towards urban forests. Okay, so to stay on time, as conclusions, this idea of holistic urban modeling, design, and planning is only growing in importance because urbanization is only growing. There's only more and more people going to cities. And generating these plausible urban geometries without assuming a dense, complete capture has proven to be a fundamental interest and maybe can transcend to other problem domains. And many cities worldwide are interested in this, and I've given a bunch of talks in different cities and countries promoting this research. So just touching on current and actually future work is, we also try and look into solar energy by understanding where roofs are automatically and be able to propose large-scale, city-scale urban planning tools, solar planning tools for your city. We're also developing kind of a AI engine to generate urban layouts at city scale. We've also applied this a little bit, starting to apply this to computational archaeology. So, it's kind of the same thing in an archaeological site. Maybe only 5% of the city is present. The other 95% of the site is gone. It's not because we can't capture it, but actually because it's been disintegrated So we have at least the first result where we take footprints of cities and generate plausible completions much better than competing ones. And our ultimate goal would be like, if we only have this lift, how could we infer this 3D structure here automatically? So this is done by a human. And of course, we could generate something completely hypothetical, just make it up a la Hollywood. But really, we want to generate something based on this partial information that's numerically kind of reasonable and proven to be a likely version of what this was 2,000 years ago. And also, we're trying to get into urban agriculture and see how we can help with the agricultural fields in a similar philosophy. Anyway, so that's my quick summary. Here's a website. And if you have any questions, I'd be happy to receive them.
Actually, can you hear me?
Yes, I can hear you.
Okay. Actually, I have a couple questions. In the last slide, you mentioned about your work on the agriculture. And so actually, compared with urban buildings are very structured, and agriculture, forestry are somehow much less unstructured and compared with buildings. And how do you consider the performance in comparison between those kind of forestry or the agricultural crop field and with the urban field?
So let me first answer for forestry. So we are working in urban forestry now. And yes, it is less structured, as you said, but there is a structure. So trees in a city do not appear randomly. Rather, there is some reason for them being around. There might be small forests, in which case competition for resources maybe dominates why the trees are there. But there's a lot of trees along the street, trees in backyards, trees in the middle of urban locations. These are actually there for planned urban rules. So we don't need to know these rules. There actually is a structure to their location, sizing, and so forth. So that's what we're trying to exploit in urban forestry. And we've had some good success so far. Now, the forestry that's away from the city, we have less experience with it. The fact that CVPR paper we have here this year is our first dabbling into forestry away from the city. So we're trying to learn more about how to address that issue. Now, with regards to agriculture, I don't have any concrete papers yet, but we're trying to see how we could apply this sparseness idea to agriculture. Again, if you have to model everything in every detail, I'm going to say, sure, we can do stuff. But how can we not assume that? And I don't have a concrete answer for agriculture yet. For forestry, we do have some answers.
Yes.
Hi, thank you for your good presentation. I'd like to know that what is an urban ecosystem in the prevention of the fire, forest, or wildfire in the summertime from Canada to North America?
I'm sorry, I'm not sure I understand what the question was.
Okay, this ecosystem in the prevention of the wild, W-I-L-D, wildfire in the summertime from Canada to North America, not to go into the labor. Thank you.
So dealing with wildfires in and around cities. Yeah, we haven't really addressed that area. That's pretty exciting to think about, right? Maybe be able to predict those areas that are most likely to maybe be under drought and then have a wildfire, and then how will that wildfire spread and what damage could it cause? There is potentially work in that area, but we have not worked yet with wildfires. But maybe we could talk afterwards offline. That would be an interesting area to try and learn more about, I would think.
And maybe, sorry about that, maybe a good suggestion to the federal government, to Canada or US. Once you saw the coming out of the wildfire, you can cut a long path to avoid the wildfire come to the neighborhood.
Yeah, I understand. To come to neighborhoods. Yeah, I mean, I haven't really worked in that area, so I can only imagine useful tools. And I think it would be something exciting to work on. I do know of some work that some colleagues of mine were doing with regards to like smog and pollution and air pollutants and aerosols moving through a city, and how you could alter the city design to try and reduce the effect of smog and air pollutants. So that is something I know about, but there might be a similar thing with forestry and fires, but I haven't worked there. But I would
Not the
like
point
to.
Sorry, stop you. Not the point of reduce, just a prevention, not to just as by engine or help other country to help Canada. You can make a path about to avoid that go to others. Sorry.
Oh yeah, that would be great.
Thank you. Okay. Thank you very much. Time is here, and if there's any other questions, I think Dr. Daniel Aliga would be very welcome to answer questions through emails. With that, we will have our second speaker.
Put it up here.
Probably it's easier.
Yeah.
So while setting up, let me introduce our second speaker on the Dr. David Crandell. He's a full professor in the University of Illinois, Indiana, and he's currently the director leading the IU Indiana University Computer Vision Lab, and he has received many awards, including the prestigious SF Career Award. And also he has quite a lot of grants from different agencies like DOD and Facebook, Google, Kodak, and Indiana University. And he obtained his degrees from Cornell University and spent a couple years in Kodak. Okay, thank you very much, Dr. Crandell.
No problem. Thank you so much. Okay. Yeah, thank you so much for the invitation and the introduction. And Goyo told me that I could talk about whatever I wanted. And so I thought I would talk about, I'll tell you a little bit of a story about how I started thinking about like location, geolocation stuff at global scale, and then recently have been thinking about it at an extremely small scale. And I wanted to sort of tell you about that and see if I can get you sort of thinking about the possibilities there. So I started being very excited about geolocation stuff about 15 years ago when Flickr became a thing, and suddenly images that are geolocated and time-stamped were widely available. And so this was just as I was becoming a postdoc and going on becoming faculty member. And is it okay? Oh, my face. Oh, I think I have to be over here is the problem for this camera. Because it's that camera. Yeah, it's that camera. Yeah. I mean, I could use my camera. Well, okay. All right, here. I'll turn on my camera. Okay. Okay, here we go. There we go. That's better. Okay. So we have this series of papers in my lab where we were looking at what we could do with this geolocation data, this geolocated images. And one thing literally is to predict the location of where an image was taken, and then using the GPS coordinates as the ground truth, but try to do that based only on visual information. Another way of using the geolocation GPS coordinates was as a hint in 3D reconstruction at very large scale from hundreds of thousands of images. Another way was to use the images together with text and the GPS tags in order to sort of do data mining on geolocated social photos, to do things like identify what are the most popular tourist places on Earth and what do they look like based only on analyzing this data. And then we had a whole series of papers where we were trying to use this social media image data in order to tell things about the world, such as like how global warming was affecting things like where flowers were flowering and when they were flowering, or where plants were, or how animals were migrating and things like that. And in the context of all of this, we also had multiple papers about like how people move through space and using social media data in order to do that. And yet what became sort of frustrating to me was that even though there were sort of millions, billions of images online that people had taken that were geolocated, it's actually a very sparse representation of all of the possible places on Earth that you could be at any moment in time. And so the sort of amount of data that we could collect here was highly biased towards places that people take a lot of photos. And so we got to thinking about using wearable cameras instead. So if people wear wearable cameras and they're wandering around the world, you get this very dense perspective of where it is that they are, what it is that they're looking at, what it is that they're paying attention to. In some contexts, this can be fun just for like taking pictures throughout your day. So you can imagine some future world where no one is holding up cameras to take pictures anymore. They're instead wearing cameras, and the camera's kind of taking a picture periodically throughout their day. I did this one summer and I got all these cute photos of like, you know, me and my pet bird that I would have never been able to take if I were just holding up a camera like that. But more importantly, like these cameras, for example, are now very common in the context of robotics, in the context of self-driving cars, where you literally have a camera in front of an intelligent agent that's trying to make decisions about the world, whether that's things like detecting and activities in self-driving car videos, or whether it's trying to predict the trajectories of where people and cars and other objects will be in the future, given the fact that the camera itself is moving in addition to the people, which makes this a quite challenging problem. Or whether it's, for example, trying to predict anomalies in videos by looking for actions that you don't expect are going to happen, like that one, and anticipating them far enough ahead of time that you could take corrective action. But actually, anyway, this isn't what I wanted to talk about. I just wanted to explain how we got interested in wearable cameras in this context. Because even though putting a camera in front of a robot or in front of a vehicle is technically a first-person perspective on the world, things get much more interesting when you actually put these cameras on people. Because when you put them on people, you are actually seeing what they see moment to moment throughout their day, what they're paying attention to. And I would argue that this is like the central problem in computer vision, because the whole goal of computer vision, presumably, is to replicate humans and animals' ability to see the world. And so that first-person perspective is extremely, extremely important. In some sense, vision has no meaning unless there's an observer, an embodied observer in the world to do that viewing. And so, like, compared to the self-driving car videos, for example, if you put a camera on someone who's say going for a bicycle ride, you get many more complicated views. You see their hands, you see what they see moment by moment, you see their activities, their interactions, and so on. These are all videos I took while riding my bike during the pandemic, which I did a lot of because there was nothing else to do. And yet, and so if you're, one of the challenges of doing this research in this area, first-person vision, has been lack of egocentric data. To some extent, we now have a solution to that. You may have heard of the Ego4D data set, which was launched last year at CVPR. It has some 3,000 hours of video from over 800 people and many locations on almost all continents on the world. Collaboration with a huge set of universities, and it has ground truth annotations for many, many things: narrations, objects, actions, interactions between people, and so on. It also has quite a bit of multimodal. Some of the videos have quite a bit of multimodal data, things like narrations, IMU data, gaze data, audio, multiple cameras, 3D scans, and so on. The data that we collected at IU as part of Ego4D has a lot of social interactions in it. So interacting people where you have things like people moving around a space, people manipulating objects, people interacting with each other with their hands, talking to one another, and so on. But actually, not even this is what I wanted to talk about today. What I wanted to talk about is the sort of use of these wearable cameras and computer vision techniques in the role of actually doing science, of sort of understanding a very important system in the world. This is kind of a cool picture. It's from an article from back in 1945 when Vannevar Bush, who was a sort of prominent person in the US government who had a role in setting up National Science Foundation and other things. He wrote this article in 1945 talking about what he thought would be the future of technology. He famously predicted things like the internet and something he called the Memex machine. But one of the things he suggested in this article is that in the future, people would be wearing cameras like this one on their forehead. And he envisioned it something like a chemist or biologist in the lab, instead of having to like furiously write down the results of all their experiments, they could instead have this camera that would be recording everything they saw. And, you know, this is now possible. I love the little wire there. He didn't foresee wireless, but he foresaw the rest of it. Now, we're not using this in the lab for chemistry or biology. We're instead interested in a much more important system. Arguably, this is one of the most important systems in the world. It may be the most important system for us as computer vision researchers to understand. And that important system is like my little nephew or any kids. Because if you think about it, little kids at the age of about 12 to 24 to 36 months are learning how to do all of the vision tasks that we want to learn how to do in this conference, including how to navigate the world, including how to recognize the names for objects, including how to build language, and so on. And so understanding these kids is sort of key to what we are trying to do here. And so at IU, we've been working for many years in sort of this interdisciplinary collaboration between folks in computer vision like me and folks in psychology and developmental psychology to understand no longer like a global level about how people move around, but instead at a very local level about how kids sort of navigate a small environment in the context of learning. And so this is a typical experimental setup. Those two folks over there are Linda Smith and Chen Yu, who are developmental psychologists who've developed over the last many years a paradigm where they can bring kids and parents into the lab. The kids and parents can wear eye gaze trackers, they can wear cameras, and then they can wear other kinds of sensors. And then you get sort of a moment by moment view of these two people interacting together in some context. A typical context might be just free play context, where they're brought in, they're playing with toys in an environment. And the kid, who's only like 18 months old, is still learning the names for new objects, they're picking up language. And so in the context of playing with toys, the parent is saying things to the kid is maybe repeating some of those things. They're learning over time the names for these objects. The data that you get from from this experimental paradigm is very, very rich. So you get both the kid's point of view on the left and the parent's point of view on the right. And those crosshairs are, of course, showing where each person is looking at each moment in time. Now, on one hand, at a purely superficial level, this data of kids and parents interacting with each other is super interesting and super challenging from a computer vision standpoint, because the kids and the parents are the camera's constantly moving all over the place. The kids don't have great control over their motor skills yet. They're looking at kind of random things. There's just a lot of noise here in a really interesting way. And so there's all kinds of interesting just like computer vision problems that we have studied, regardless of the underlying science here using this data. Things like hand detection, things like joint hand pose detection, because of course, what you do with your hands is extremely important. It's important for us as we go about the world, interacting with the world, sensing the world. It's particularly important for kids as they are learning to manipulate the world and learning language and learning how to recognize objects. And things like modeling gaze. So again, not where on earth people are anymore, but instead where are kids looking in the field of view. And so we have work that's trying to predict in a first-person view where it is that somebody is going to be looking at any moment in time. The red crosshair here indicates where they were actually looking, and the blue crosshair indicates where we predicted it. But the underlying, from a sort of scientific point of view, the underlying mysteries are, how is it that kids are so good at learning to see the world and learning the names for objects? Kids, it turns out, according to the literature, are amazingly efficient one-shot learners, way better than computer vision one-shot learners. They can learn dozens of words, new words each day. And they have this amazing ability to generalize. So it's like they'll play a bit with a toy like this fire truck. They'll hear the word fire truck. They'll learn that that's a fire truck. And then they'll be able to generalize to essentially every other fire truck that they ever see throughout the rest of their lives. And sure, they make mistakes sometimes, just like our vision algorithms do. But their generalization ability across different contexts, across different types of fire trucks, different modalities, and so on, is really quite amazing. And the kids are also solving a very important problem that we struggle with in computer vision, that of weak supervision. So let me give you an example. Let's say that you are a learner. You could be 18 months, or you could be whatever you are right now, 30 years old. And this is your viewpoint. You're looking at this thing. That's your mother, say, on the other side. And the crosshairs show that you are looking at her mouth right now. And she says the word pegbo. And you are like, great. What does that mean? I know this is some new word I'm supposed to be learning, I guess. I'm looking at her mouth. Is pegbo her mouth? Is it the name of the thing that I'm holding? Is it the name of the whole thing she's holding? Is it the color of something? Is it the environment? Is it the temperature? Like, what is this word? And yet, through this very weak supervision, kids, all of us, were able to acquire language and make these associations between words and objects, solving the referential uncertainty problem of how to map locations in the world to objects. And so the question is, how do people do this? Well, one obvious thing is that they probably do not use AlexNet to do this. So in our head, we probably do not have AlexNet. We probably don't have transformers. We probably don't have ResNet. We may have something that has similar themes, but clearly the hardware is different. I'm not talking about the hardware here. We're going to ignore the hardware. Instead, we're going to look more about like the data, the tasks that they're trying to solve. So kids do not learn what a car is by downloading 10 million images from ImageNet of a car. Instead, what they get to do is they interact with a relatively small number of cars in an environment, like a little toy car. They get to see it in lots of different contexts. They get to see what happens when they move it from room to room, when they beat it with a hammer, when they throw it at their parents. They get to see how it changes over time. They also get to manipulate it. So they get to manipulate these objects. They get to hear, they get multimodal sort of information from audio, from parents, from their own audio, from their own utterances. They get tactile feedback, they get smell, they get other sensations. And maybe importantly, they also have, as we all do, foveated vision, so that at any moment in time, they're only getting sort of high resolution data from one particular location in the image. And this may be very important because if they're looking at the right thing when they hear a label, that might help them make that label object association more easily. And so with this in mind, I'm just going to tell you about a couple of studies that we've done related to this joint area of understanding like how kids learn the names for objects and how sort of location cues within their field of view is important in doing that. And so the first study here, we brought 26, actually for all the studies here, that I'll show you, it's sort of the same setup. We bring in 26 child-parent dyads, so a parent and a child, into the lab. There's like a home-like environment with toys that are around the room, and the kids and parents are just told to just play in the room as if you were, at home, play with toys naturally. The kids are from 15 to 24 months old, which is when kids are learning words for objects. The objects look like this. They're kind of visually distinctive. They're kind of fun. And then what becomes clear as you see this data, so then we can take this data and we can use computer vision on the very simple object tracking on the head cameras of the kids and the parents, and we can then get all of the views that they saw of all of these objects from the parents' view and from the kids' view over time. As you can see, from the kids' point of view, it's very highly dynamic. Objects come and enter and leave the frame. Sometimes they get very big. They become socially dominant. They become spatially dominant. Sometimes they get smaller. Sometimes they leave the frame completely. As you can see, there is a lot of manual manipulation, both by the parents and the kids. And that turns out to be very important, as we'll see in a moment. So it turns out that in this first set of experiments, we looked at individual objects like say in this case, the red helmet. We looked at all of the instances that all of these kids saw on the left and all of the instances that the adults saw on the right of the same object. And it becomes pretty clear that the views from the kids' point of view and the adults' point of view are quite different. You can just sort of see in the summary. And so that raises an interesting kind of question, which is, let's say these are not kids and parents, but they're two agents in the world, and they've been sent on a mission to collect training data of these toys. Which is collecting the better training data, the kids or the adults? And we can actually do a computational experiment to figure that out, which is what we did. So basically, we trained two CNNs, one on the data that was collected by the parents and one on the data that was collected by the kids. So those form two separate training data sets of two agents that are exploring the same environment at the same time. And then we train model A based on the parents' views, model B based on the children's views, and then we test these two models on some other data set that was basically the same images collected in a lab setting, like on a turntable, so independent from the first person view. And then the question is, who collected the better training data, the kids or the parents? Well, it turns out that no matter how you slice and dice the data, the kids' training data is always better for training the deep neural networks, which is kind of interesting. I mean, it suggests A, that there's something different about the views the kids and parents are getting, but then B, that whatever the kids are doing is actually better for visual learning. And that might be an important piece of feedback for us as computer vision people to understand what is the difference between these two data sets and how would we replicate the same thing in computer vision. And so there are some obvious differences between the two data sets. One is that the kids tend to get larger views of objects, which is perhaps not earth-shaking because, first of all, kids have shorter arms, so the objects are bigger, and they're also closer to the floor in some sense. And so we see that there's sort of this much larger, there's much greater visual saliency of some objects in view than others in the child's view. But that doesn't entirely account for it. We can control for object size and still find that the kid's view is better than the parents. And so then the next question is, well, what else is different here? Well, to answer that, or try to help answer that, here's a visualization where we took another object. These are all the views of another toy, the blue car. And we used some simple technique, multidimensional scaling and some feature space to visualize what the toddler's point of view looked like and the kid and the parents' point of view looked like. And what you can see immediately is that the toddlers are collecting much more diverse examples, much more diverse perspectives and viewpoints of these objects, which is, of course, also probably not earth-shaking. I mean, if you think about it, when I hold a cell phone, I typically look at the front of it because I want to see what's on it. When kids who are still exploring the world are manipulating objects, you know, they're sort of looking at things from many different unusual perspectives, and so they get those viewpoints that are less common. And so in both cases, we sort of find that there's kind of this core set of very canonical views that the kids and the parents are getting. But there's also then a much larger kind of tail of very diverse views that the kids are seeing and not the parents. And you can measure this in multiple different ways in terms of like the visual diversity. This is a measure of object dissimilarity on the x-axis, and basically it's showing that parents get much more similar views than the kids. And so the kind of conclusion here is that, you know, toddlers are spending many hours every day playing with toys. They're actively manipulating them, and in doing this, they're basically creating training data for themselves, for their own visual system. And based on the way the embodied like kid system works, because arms are shorter and they're fumbling with things more, they get more diverse data for the children than for the parents. We have some results where we tried to kind of better quantify like what is the difference between, what exactly is the difference in diversity between these two sets. I'll just sort of give you a highlight here. But the idea is that it seems like there's some benefit for a visual learning system to have a set of very highly similar canonical examples. So you can sort of see the structure of what an object should look like. But then you also want some diverse examples that sort of show you the edge cases. And this, so we can sort of take a data set and we can create a synthetic training set with varying combinations of these two types of examples, highly similar examples and highly dissimilar examples. And I'll just show you some results here, and you can check out our paper if you're curious for more, just to sort of give you a flavor of things. These are some experiments where we again took these objects from the toy set that I showed you before. We trained various deep neural networks with different structures of training data. And there's a lot of graphs here. I'll have you focus just on the one on the right, which has 200 images per class in the training set. And what we found is that if you take the original distribution of training data that the kids saw and just sort of randomly sample it, so you have 200 images per class, and then you test the accuracy of that model on some other test set, that we get some accuracy that looks something like this. If you look at only the highly diverse examples, we get a lower accuracy. If you look only at the highly similar examples for training, you get some other lower accuracy. But if you use sort of a nice 50-50 combination of the diverse and similar examples, then we get something that approximates the kids' point of view, the data that the kids were actually collecting. Now, the interesting thing about this is that it suggests that there may be some principles in here that would help us in computer vision. And so to test this, because maybe instead of just using all of the examples or randomly sampling examples in a training data set, maybe we should be selecting them according to some kind of structure. And maybe the structure that is revealed in what these kids are doing could give us a way of doing that. And so we have some very, very preliminary results, like extremely preliminary, where we use two data sets. One is a training set selected from COCO, and another is some test images that we generated from ShapeNet. Basically, we trained these deep neural models, deep neural networks on COCO, and then tested them on ShapeNet to test like this generalizability, similar to what we did with the kids. And what's very interesting, here's another set of results here, and I'll again walk you through only the bar on the right there. What's interesting is if you use just the original COCO distribution, so you just sample randomly from COCO, You get some test accuracy on this other data set, the ShapeNet data set. That's okay. If you use only highly similar examples, then you get about the same distribution, the same results. But if you use the same distributions as we saw in the kids' data, about 50% dissimilar, 50% similar, then you get a much higher accuracy. Well, maybe not much, significantly higher accuracy. And so this is just some very preliminary example of the way that maybe we could use inspiration from what kids do as they're sampling the world in order to build better training data sets in computer vision. Very preliminary, but kind of cool. So the study of the conclusion of this study was that there seems to be these distributional properties that in data collected by kids, and that could be very beneficial for learning. Now, let me tell you about sort of two more, I'll briefly tell you about sort of two more kinds of studies that kind of, again, get back to this idea of how kids figure out like where they should be attending and maximizing learning. So the second goal is also, the second study is also a computational experiment. Basically, we took this same data from the kids and the parents who are playing together, but instead of using hand-labeled labels as the training set, we instead used the utterances that parents naturally said as they were interacting with the kids. So, for example, you know, the toy play session is going on, the infants are seeing one thing, the parents are seeing something else, and in the same environment, and the parents are just talking to the kids. Here's a little ladybug, says one parent. It's a snowman, how about this, and so on. So then whenever we saw one of those object names in the utterances by the parent, then we took the frames right around that utterance as training data for our computational model. And we know where the kids and the parents are looking in the field of view because we have gaze tracking, so we can use sort of a bounding box around that point. And again, so many details that I'm just skipping because I'm trying to give a high-level overview of the exciting results here. What we found was that, yes, the model could actually learn the names for the objects based just on these parent utterances. But interesting, we again found that the child data was much better for doing this than the parents' data. So if you train the model on the parent data, the accuracy kind of asymptotes, but the child data continues to increase over time. Now, let me now tell you about a third study, which tries to sort of take this one step further, which is that if there is important properties in the field of view of the kid that yields sort of or promotes good word learning, then another question is, can we actually predict whether the child will learn the word? So in other words, you can do an experiment where you test the child at the beginning of the experiment whether they know the word for an object. Then you can have them play with their parents. And then at the end, you can check whether they have learned the name for that object, whether the child has learned the name for the object. And then we can build sort of a computational model to try to estimate whether the child will learn the name of the object given the data that they saw, given what the parents saw and what the parents said and what the child saw. And the answer here to cut to the chase is actually, yes, the model could predict when the kid was going to learn the name of an object. And so this, you know, not with 100% accuracy, but with greater than 50%, greater than chance accuracy. And so this suggests that there are some signals in the raw sensory data that tells you whether or not the visual learning for the child will be successful. And that probably has to do with where the child is looking, what the parents said, and so on. And so to get that down one step deeper, I'm finally going to talk about one more quick study very briefly that sort of tries to tie together this idea of where kids are looking, where they are attending to, and where they should be attending to in order to solve the referential uncertainty problem that I talked about at the beginning. So it turns out that people know in psychology that moments of joint attention for parent and child on objects are very important for word learning. In other words, if I want to teach you the name of this object, it turns out that one of the best moments to do that is when you are looking at this object and I am also looking at this object. Now, the issue is that the child is just a child who is just kind of like being a child. So they're not necessarily doing what they're supposed to do. The adult is just kind of, in the moment trying to play with this child. And so how is it that these two actors together can develop the right environment for word learning? And how is it that that system is so robust? Like all of us in this room, no matter how good or bad our parents were, managed to acquire language. It's really quite stunning that we were able to do this. And so one of the important kind of principles that the developmental psychologists I'm collaborating with have suggested is that it all has to do with manual action. So it has to do with the fact that parent and child are embodied and they can manipulate the environment and they can manipulate the objects in the environment. And basically, when parent and child can manipulate environments in the objects, they then often create visual dominance. So that means that they make it so that from the child's point of view or the parent's point of view, the object is salient in view, it's large in view, which then causes the child or parent to look at the object because it's large in view, and that gives you joint attention, which is important for language learning. And so I'm not going to talk about all these details because we're running out of time, but basically you can get then over time very high fidelity data about moment to moment, what is everybody looking at, what are they attending to, what are they saying, what are they manipulating, who is holding which objects, and so on. So a lot of this, we can use computer vision to do some of this. I mentioned the hand detection and the hand object pose detection exactly because we wanted to detect objects in hands and how they're being manipulated and so on. But I'll just sort of cut to some of the interesting results here. Here's one interesting result that's looking at the proportion of time that a child is looking at the visually dominant object, the percentage of time that their attention is on the visually dominant object. Well, it turns out that if the parent and the child are both holding that object, they're both manipulating that object, then there's a very good chance that the child is attending to the object, assuming that it's large in the field of view. However, just because an object is large in the field of view does not mean they're attending to it. In fact, if no action is being applied to this object, if neither a parent nor child are holding the object, then it turns out that there's a very low chance that they're looking at that object. Very poor moment for language learning. And if only the infant or the parent are individually manipulating the object, there's still quite a good chance that the child is looking at. So the sort of takeaway here is that when visual dominance is created by manual object manipulation, the children are very likely to attend to the visually dominant object, whereas they're not likely to attend to a visually dominant object that is not being manipulated. And similar results hold for the parent as well. And so this indicates how there's one pathway towards establishing these moments of joint attention. It's about people being able to manipulate objects that causes the child and parent to be to attend to a particular location in the field of view, and that creates a good moment for word learning. Okay, I am out of time, so I will just conclude with a few thoughts. So the conclusion for this fourth study, I think, which is really very interesting, because you have this system of parents and adults who are trying, kids and adults who are trying to the parents just trying to keep the infant from crying and like get through the day, but they're also trying to teach the world, they're trying to teach the infant how to see the world. And it turns out that there's these very like robust, low-level kinds of processes that can support that, where both infants and parents' action and joint play creates visual saliency of objects, and that supports visual attention. And it's interesting that there's sort of multiple pathways to be able to do this. So it could be that the parent is holding, it could be that the child is holding. Both of these things can lead to great moments for learning, which helps to explain why there's sort of this is such a robust system. Okay, so my high-level takeaways are, first of all, I think the first person perspective of interacting children and parents is really challenging and it's interesting for many computer vision tasks. And I think, including things like visual odometry, tracking, object recognition, attention estimation, saliency estimation, and so on. But second, and I think understanding like how children solve these tasks is important, both societally, like so that we gain insight into developmental psychology, but also how to help kids who are struggling, how to help kids who are struggling with visual and language learning, for example. But lastly, I think that this kid-parent interaction kind of task, even though what I'm showing here is very, very preliminary, very, very first steps, I would argue it is the natural context to study how best to improve computer vision, because it's basically investigating the world's best learning system, which is the human child. And with that, I'll just say thank you very much, and I'm happy to take any questions.
From the audience?
Thank you for your presentation, David. I'd like to know that Microsoft Bill Gates has said that 18 years old, due to the ChatGPT, no more teachers. Okay, I put this one into your presentation. If you can get the parents and kids in mutual inductance on going into the ChatGPT learning instead of the garbage TV to develop their conscious mind and subconscious mind. Is it possible?
It's a good question. It's something that we've actually been thinking about, so this work and other work in developmental psychology sort of tells us what are the good moments and bad moments for learning, how best to go about it, how not to go about it. And so you can imagine building, a robot teacher that would be potentially better than some parents at helping kids learn to see the world or learn language. And so I think that is kind of an interesting direction to go. And there's all kinds of ethical concerns. There's all kinds of other problems that it might bring up. You mentioned garbage TV, which I agree, a lot of TV is garbage. However, it is actually the case that, in developmental psychology, they study how kind of kids over time pick up the patterns that help them do visual recognition. And in many ways, it is kind of similar to the way we think about it in computer vision, where they start off with sort of unsupervised learning at very young ages. So at very young ages, they're just sort of watching the world around them. And it turns out that we think that that's very important, even though they're not getting good labels for things at that point. Just being able to see the way the world changes visually over time turns out to be important. And then as kids get older, they start crawling, they start walking, they start, doing other things. And so, it could be even the garbage TV is actually important. It could be helpful for helping kids, build up language and build up visual learning. And whether that is better or worse than ChatGPT, I don't know. Interesting question.
Okay, I'm sorry to correct my wording. Garbage TV advertisement.
Advertisement. Yeah, well, yeah.
And then I want to know that can something change on the kids 3 to 10 years old or conscious mind?
Can something change?
Yeah,
because of TV?
Faster. By the mutual inductance of their parents' education.
Good question. I have no idea, but it's a good question.
Sorry.
Oh, no, good question.
Thank you, Professor, for interesting talk. So it's very interesting to know, from children perspective, it's a good future learner, they learn from this diversity, more diverse data. So I'm thinking because like now when we want to get higher accuracy, we want label data. But from this study you give, would that be are there any way to help our big model in self-supervised training mode? Are there have you thought about any new mode that can like help develop this like foundation model or something?
Yeah, good question. I mean, so a couple of answers. There's been some initial work that has used like egocentric and even kid video data as like a, you know, part of pre-training for in some self-supervised learning kind of framework. And it's very preliminary. You have to, there's a lot of caveats and stuff, but it seems that that data could be particularly rich and do a better job than just like using video data from YouTube or something, if you control for the size of the data and stuff like that. It's very preliminary work, but I think that that's really interesting because it could really be that like the kinds of scenes that kids see as they're just playing with the world is more helpful than like, you know, sitcoms that you download from YouTube in order to help with pre-training. So I think that's one conclusion. I think another conclusion might be that in computer vision, we don't typically, at least I don't usually think about the structure of the training data itself. So we just sort of think that more data is better. You know, so if you want to build a better object model, you just ingest more and more and more data. You don't really, for that object, you don't really worry about the structure of the data. And I think that that's very different from what kids do. So kids do not get 100 million images of cars from the web to learn how to learn what a car is. They instead get a very different set of distributions, which is like a single toy car that they play with and see from lots of different perspectives. And so that structure of knowing that it's the same car and different viewpoints may be actually really important for them to build up invariance about, like, you know, how the same object can appearance can change in the world depending on lighting, depending on viewpoint and stuff like that. That might be really important. And there might be other structure that's important as well that we don't know about. So it's a really good question. I don't have like some silver bullet, exciting, groundbreaking answer.
It's very answer. Thank you.
Thank you. Sure. Sure.
So you have used children, and the parents to study, and I also see some research on very inspired study, like using pet, dog, and how you think about what is the difference, or whatever you have done, could we just manipulate that and on pets and like pets and their master?
Yeah, good question. There is interesting work that's using animals. I haven't done any of that. There is someone at IU named Justin Wood who does really interesting work where he raises little baby chickens in virtual reality environments. And so you can do these really interesting things like, you know, the chick hatches in a virtual reality environment and you can control exactly what it sees from the moment that it's born. And you can do things like, you know, if a chick never sees an object from multiple points of view, are they still able to estimate like what the 3D object looks like? And, you know, stuff like that, and very controlled experiments, which of course you can't do with humans because it's super cruel, but you can do it with chicks. So I think there's interesting work to be done there. There are differences, of course. I mean, chicks don't really have language in the same sense that we have. They don't have visual cortexes in the same way that we have and so on. But I think there's interesting things that can be done there.
Simple question.
Sure.
Sorry. Okay, have you heard about the neural-optical?
About the
neural-optical connection from the human being, the mind to the eye to be faster.
Oh, I don't know.
That means that you are in the vision, right?
I see. Yeah, I don't.
About that in US. Sorry.
No, I don't think I know anything about that.
Yeah, neural, N-E-U-R-L, because you connect the mind to the eye, that will do the thing faster, like you control the F-16 or the airplane.
Interesting. Yeah, I don't know anything about
the
that.
assembly language. 1010.
Oh, thank you. I'll check that out.
I learned it from Tom Cruise.
I see. Okay, I'll check that out.
Okay.
Thank you very much.
So next, after that, they give one more.
We can share from Zoom, so you don't have to. Yes.
So let me introduce our two speakers, and they will give a combined presentation talk and representing GM, General Motor Company. So the first one is Dr. Xingyu Du, and on my side, and he received his bachelor and master degree from Tsinghua University in China, and the PhD from Wayne State. And he has been working on with GM and since 2010, and currently is a staff researcher in Vehicle System Research Lab. And his research has been awarded 2 Best Paper Award. And his research has been implemented in more than 2 million GM vehicles and received the Best Innovation Award, which is also called Boss Catering Award from GM. And he has been he has been associate editor for multiple journals, including Journal of Intelligent and Fuzzy System, and Attribute Transactions on Fuzzy System, and is very excited to hear his talk. And the second researcher is Dr. Yao Hu, and he's also a staff researcher in GM. And yeah, and he received his bachelor degree from Fudan University in China, and the master degree from Chinese Academy of Science in 2007. And later, he received his PhD from Kentucky University. And his research has mainly been on online LiDAR to vehicle alignment, and works on online camera and vehicle alignment for ultra cruise in GM vehicles. They will give presentation and together and representing GM.
Okay, thank you, Gui, for the introduction, and good afternoon, everyone. So next, we are very happy to present our recent progress on the online LiDAR alignment. Before we dive into the details of LiDAR alignment, I would like to provide a brief overview about General Motors and also its products related to the sensor alignment. So as you may know, General Motors is the largest automaker in the United States. In 2022, GM sold more than almost 6 million vehicles globally, and over 2 million vehicles sold in the United States alone. Okay. GM's headquarters is located in Detroit, Michigan, and GM has the. Oh, okay. Okay, yeah. Yeah. I think now it's good. Yeah, so GM has manufacturing operations across 6 continents. And our vision at GM is basically 3 zeros: 0 crash, 0 emission, and 0 congestion.
0 waste.
What's that? 0 waste. Those 3 are our main goal. Okay, we have a lot of other things: 0 failure, 0 defects, but those 3 are currently the main goal for GM. Yeah. Okay. So in terms of 0 crash, we believe that the autonomous driving is the way forward to eliminate human driver errors. Okay, so at General Motors, we have a parallel path to bring hand-free driving to the market for individuals. Currently, we have Super Cruise available in our products, and soon we will introduce Ultra Cruise. Okay, so these technologies aim to provide true hand-free driving through experience, and simultaneously we also work with the Cruise to pursue the fully autonomous driving. So Super Cruise, which is industry first hand-free driver assistant technology, allow drivers to travel hand-free on over 400,000 miles of compatible roads. Okay. Ultra Cruise, which will be launched in the near future, offer a destination to destination hand-free driving experience and designed to cover 95% of all driving scenarios. Okay, so Ultra Cruise right now utilize a combination of cameras, short and long range radars, LiDAR positioned behind the windshield. So to fuse all the results from all these sensors, the sensor element play a crucial role. So in the next slides, we will share a short video to demonstrate the GM Super Cruise system. Okay. Yeah, GM launched the Super Cruise since 2017, and right now we have accumulated more than 60 million miles for our product. Okay. Let's move on to the sensor alignment part. So first of all, we would like to give some background about the LiDAR alignment. So LiDAR alignment, more in a more broad sense, is basically the sensor alignment. It's also called extrinsic calibration. Okay, so from the top left figure, you can see that the lowercase x, y, z define the sensor coordinate. Okay, and the uppercase x, y, z define the vehicle coordinate. So the goal of alignment is to try to find out the transformation between the sensor coordinate to the vehicle coordinate, so that we can project any points, any results from the sensor coordinate to the vehicle coordinate. Okay, and fuse them together. Okay, so normally, for small scale of vehicles, like less than 100 vehicles, test vehicles, we can do sensor alignment regularly and manually, right? It's very easy in the service bay with some alignment stations. But for large fleet of vehicles, like millions of vehicles, this is not realistic. So we have to go to the online sensor alignment route. So basically, when the vehicle is driven on the road, we will generate the extrinsic calibration automatically. Okay, and of course, to do it in the real environment compared to the service bay, the difficulty is totally different. And there are a lot of real challenges. For example, the environment disturbance and the random noise. For example, the severe weather, right? Snow, rain, or road is wide. Those are the real challenges for the online alignment. And also the sensor accuracy itself is also an issue. It may impact our alignment performance. And also when we do offline alignment in the service bay, there is almost no compute limitation. But if we do it in the vehicle, and considering we also have the Ultra Cruise, Super Cruise, those autonomous driving features, right? Then the compute resource is very limited. So when we design a system, we need to consider this limitation. Okay. So what's the relationship between the sensor alignment and visual odometry? So here you can see that there is a famous hand-eye equation, AX equal to XB. Right? So A basically is the sensor trajectory. Okay. Normally we use the point cloud registration or image matching. We can find out A, and the X is basically our alignment, extrinsic alignment, right? And the B is the vehicle localization results. Okay. So here from this equation you can see that if we know A, and if also we know B can be measured from GPS and MU, right? Then this is an alignment problem, right? Basically, we just try to solve this equation, try to solve X with given A and B, right? And if we don't know, if we already know X, we do finish the alignment, right? And we estimate A, then we can estimate B as well, right? This is a localization problem, okay? And compared comparing the sensor alignment with the visual odometry, we know that normally for the sensor alignment, right, it changes slowly than the localization, so it's less sensitive to the time. Okay, but you see from the equation, you can see that if you want to solve X, the excitation condition is more restricted. Okay, then calculate B, because B you can easily, move the other X to the other side. You can easily calculate, but for this one, it's not easy. So in our following presentation, that paper, we will show some results on what is for the vehicle drive, the vehicle on the road, right? What's the exact excitation to generate X? Okay. And also in terms of method, right, to generate X, actually there are two types of method. One method is that we need to know A, we also need to know B, then we can generate X. This is normally it's kind of hand-eye method or SLAM-based method. Another method is that we can just generate X. We know X and B, but we don't need to do A. It's called aggregation-based method. I will talk about the details in the next slide. Okay. So as you know, because this extrinsic calibration is super important to a lot of applications. So there are already a lot of papers cover different methods in this area. On the left, we show some papers using the hand-eye based method. So you can see in those methods, normally the people use ICP, GICP, NDT, or different methods, right, to calculate A. Okay, like the point cloud registration or image registration, right? And those methods can be, by minimizing the corresponding point-to-point distance, or point-to-line distance, or plane-to-plane distance, point-to-plane. There are different type of loss functions allow us to, generate this registration. And there are also other methods like EKF, factor graph, or some bundle adjustment to improve the overall accuracy of the hand-eye, these hand-eye methods. And in the bottom, we put some example figures from some existing papers. And you can see that one route, right, is the sensor trajectory. Another route is the vehicle trajectory. And then you can find out the transformation between those two. And here you see, if you see the vehicle trajectory, that 8 shape, you see why you need this kind of shape, right? The trajectory is because of the excitation. And actually for this paper, it's easy to achieve because it's kind of in a test environment. But in the real vehicle, real driving, this is very hard to achieve. The customer won't drive the vehicle in this way, right? So then that's the challenge for us, right? If we don't want to interfere customer driving, how do we generate sensor alignment effectively, right, and efficiently? On the other side is the aggregation-based method. Okay, so aggregation-based method basically is we have the point cloud from each LiDAR frame, right? We need to project the LiDAR point from the LiDAR coordinate to the vehicle coordinate using the LiDAR to vehicle transform. And then we project the points in the vehicle coordinate to the world coordinate, okay, using the localization results, GPS MU results. So, and then we aggregate all of them, all the point cloud together, okay? And then the loss function is that we need to minimize the weakness of the static object to calculate the sensor alignment results. So why is that? The reason is that when we have the sensor alignment issue, right? When the vehicle is closer to the target or the vehicle is far away from the target, the position in the world coordinate is different if the sensor alignment is wrong. Okay, so that means for certain target in the aggregated point cloud, it becomes bigger. So by reduce the volume, reduce the size of this target, we can find out the alignment. A good alignment corresponds to the smallest target in the aggregate point cloud. Then the next question is how do we design a loss function, right, to characterize the weakness of the target? So there are multiple ways in the literature. For example, the first one is distance between plane surface, right? So for each frame point cloud, you can calculate a plane, right? And then for the plane in different frames, and you put it together, you try to minimize the distance. Or like a PCA is also a classic method, that because the PCA, given a point cloud, when you do the PCA, you can get the eigenvalues, right? Those eigenvalues are corresponding to the point cloud variance. So by minimizing the eigenvalue of PCA, then kind of you reduce the point cloud size. Similarly, there are some other like distance between corresponding points, those methods. And in the following slides, we are going to show some other methods, some other loss functions that we proposed in the last several years. For the second method, aggregation-based method, because it involves the localization results, GPS-IMU, right? We need to map from the LiDAR coordinate to the world coordinate. So if GPS and IMU is not accurate, right? That always happens in the real world. Then our result may be wrong. Okay. But the good thing for aggregation-based method is this one doesn't require a frame-to-frame registration. Okay, you just simply do the projection and put them together. So compared to the hand-eye, right? Hand-eye, you need to do the frame-to-frame registration. That's one optimization. Then you need to find out X. That's another optimization. You need to have at least 2 optimizations. But here for aggregation, you just have one optimization. That's from that perspective, it's a little bit simpler. Okay. So next, I think I will invite Yao Hu, my colleague, to talk about the work we have done in the last several years. Yeah, thank you.
Yeah, okay. Thank you, Xin, and thank you, Guoyu, for the introduction. My name is Yao Hu. I will continue to cover some of our work that we did in the past few years in GM. Yeah, so this slide gives a very high-level overview. And as Xin just talked about, in the literature, there are basically 2 big categories. One is hand-eye, the other is aggregation-based. And here, actually, we tried both, and we also come up with some different ideas as well. And all of them actually are listed here. This is a summary of the past few years' work. So starting from the first one, which is the row targets method. This is actually belongs to the aggregation-based category. So this is an aggregation-based method. And similarly, the second one, the scene aggregation, is also belong to that category. And the third one is hand-eye, which is, as you just talked about, we need to get A, then get B, then we solve the hand-eye equation. The last 2 is actually not belonging to either hand-eye or aggregation-based. So I'll talk the high-level concept for each of them. So in the okay, yeah. So in the previous slide, when she gave the literature review, there was one figure showing, down below, showing the aggregation-based cloud, the point cloud. So when you have the extrinsic arrow, which is the arrow in the alignment, then we do 2 steps of mapping. We convert the point cloud from the vehicle, from the LiDAR to vehicle, then vehicle to world. Then you will have some arrows in the aggregated point cloud. The symptom basically is you have the fuzziness or target shift in the aggregated point cloud. Then we can actually leverage this property to do optimization. So the first method, the row targets, basically we use the traffic sign and the lane markings. So if you see the agenda, so actually after this talk, we have another presentation for the paper, which talks more details in the first method. But here, I just give you high-level concept. So we get those targets detection from the aggregated point cloud, and then we formulate the loss function to determine the fuzziness or target shift. Then by doing the optimization, we can determine the alignment. So For the loss function, I will talk more in the next few slides. But the basic idea is we minimize the target size and the thickness, because for the both remarking and traffic sign, we can treat them as a plane. So it's more like a board shape, the rectangle bird shape. So the thickness actually is a very good indicator. We can use that to do the minimization. Then for the scenario, we did some degeneracy condition study, which I always also show you later. For turning and straight line driving, these are two different maneuver conditions, and they can calibrate different alignment parameters. So for turning, actually it's better because it generates more excitation in terms of the degeneracy condition. So actually you can calculate the 5 degrees of freedom. That's rho pitch yaw and X and Y. We cannot do Z because for the autonomous driving application, all the motion we consider is a planar motion. So we don't have like a roller coaster motion. So the Z excitation is always insufficient in our assumption. So the maximum degree of freedom is 5. Then for straight line driving, actually it's much more constrained. So we can only do 2. One is yaw, the other is either pitch or roll, and depending on how the LiDAR is mounted on the vehicle. That's the suitable scenarios. And then for the limitations, so field of view and the localization and also target availability. So for the first one, the field of view. So as I mentioned, so this is aggregation based. So we want to monitor the target shift over time. So when the vehicle is driving, let's say starting from the location where it is very far away from the target, and then when the time goes on, it will drive closer and closer to the target. And then maybe if it has a 360 degree of field of view, then even after the vehicle passed by the target, you can still see, I mean, the vehicle can still observe the target. So if you have a broader field of view, actually the time window that the vehicle can observe the target is much, much longer. And this is good because we want to monitor the target shift. The bigger, the better. So if you have a relatively narrow field of view, then the time window will also be narrow. Then that means even though within the whole driving cycle, you observe the target shift, but because in total time window is shorter, so the shift itself is also shorter. Then that's not the ideal case for the optimization. So that's one limitation. And the second is also the localization, because as you mentioned, so we need to get the as accurate as possible the GPS IMU information for the vehicle localization results, and these are used for the second step mapping from vehicle to world. So we do want to get the accurate localization. And this becomes a limitation because in the real case, most of the time the localization has a big error or bias, and it doesn't give us the expected accuracy. And the third one is the target availability, which is very straightforward, because if you don't have lane markings or traffic signs on the road, then definitely you cannot run this algorithm because these are the requirements. Then I'll move on to the second one, the scene aggregation. We follow the exact same philosophy as the first one. The only difference, we extend to general object. So basically we remove the one of the limitation of the first algorithm. So in this one, we don't require the target to must be the traffic sign or lane marking. So we actually extend that to more general targets. And here in the figure at the bottom, this is just an example I gave. Again, it's the fuzziness in the aggregated point cloud, but these are the trees. So just on the road, like any random environment. So these, you can see, they are still showing this fuzziness or target shift property due to the extrinsic error. So in the second method, basically we come up with an idea to formulate another loss function to capture the fuzziness for general target. Then in this case, we can still do the optimization based on this to get the optimum extrinsic parameters. So this is the second one. And the same thing here is for the suitable scenario, we only do this for turning, but as you know, this can also be done in straight line driving. The only thing is, again, you get 2 degrees of freedom instead of 5. The reason is because right now we extend to the more general targets. So usually it's very easy to get. It doesn't, we didn't run into the scenario that we always, have insufficient target. So that's why we think, maybe 3-line driving we don't need. The turning is enough. So, but technically it can also be done in the 3-line. And the same thing for the limitation is still aggregation based. So the field of view and the localization accuracy is still the limitation for that. Then move on to the third one, which is hand-eye. We basically, I think Xinyu also mentioned the high-level concept. So we measure the LiDAR trajectory using registration, and also we use the GPS MU to measure the vehicle trajectory. Then we optimize the consistency between these two to get the alignment. Turning is also needed because, again, for 5 degree of freedom, that's the needed maneuver condition. And sensing for the limitation, the sensor quality definitely, because right now for the hand-eye, we do need to calculate the A matrix, which is the frame-to-frame registration. So it's very sensitive to the data quality. In the aggregation, we don't do frame-to-frame. So that's why it has a little bit robustness or tolerance on the error of each single frame. But here we do need to calculate A. So it's relatively more sensitive to the sensor data quality. And again, because we also need the B, which is the localization. So B accuracy still is a constraint. And then the feature availability. Again, this comes to the registration, because if you want to register 2 frames, you do need features, enough features. It could be plane, it could be edges, whatever you define. If you driving on a totally empty space, then you don't get enough features. Then you will fail in this registration task. So then move on to the next 2. So the last 2 actually are also very similar. But overall here in the last 2, we don't do either aggregation or hand-eye. So they are totally new. We define them as prior knowledge based. So in these 2 methods, we don't use GPS MU to infer or indicate the vehicle pose. Instead, we use some prior knowledge. So one example is basically the fourth one. We call it ground method. So the ground surface, we can use our prior knowledge to make the assumption that statistically, when the vehicle is driving on the road smoothly, the vehicle body will be in parallel with the ground surface. So this is one way you can indicate the vehicle pose or the vehicle Z direction, which is the up direction. And actually this gives you roll and pitch. You give 2 degrees of freedom. And similarly, follow the same philosophy. Another prior knowledge we can leverage is the landmarking direction, because supposedly if you're driving straight on the road, statistically the vehicle heading direction is in parallel with the landmarkings. Then in this method, basically we detect the ground surface and the landmarkings in LiDAR data, which is basically represented by the LiDAR coordinate system. Then with these 2 vectors, one is the ground normal vector, the other is the landmarking direction vector. With these 2, we actually indicate the vehicle pose in the LiDAR coordinate system. So in this way, we get rid of the requirement for the GPS and MU. This can totally be done in the with LiDAR data. So we don't require GPS and MU. So that's one benefit of that. But the other thing is we do require 3-line driving, because if it's turning, then definitely the landmarking doesn't indicate the vehicle forward direction. And for the turning, there may be some suspension change. So the vehicle body is not in parallel with the ground surface as well. So given all this, so this method requires 3-line driving. The good thing is, the limitation again, the sensor quality, because right now it's also very sensitive to the detection of the targets for each single frame. And then the sensor quality, because in our real data, we do see some like a LiDAR intrinsic distortion, which gives the not flat ground surface, which gives some error. And this actually indicate that we do need a certain requirement on the data accuracy. And also the target availability. Again, as I mentioned, if let's say the land marking is not observable. It's maybe covered by snow or, just in some subdivision, you don't have land markings, then definitely you cannot run this algorithm. Then comes the last one, registration. This registration is slightly different from what we talk about in the hand-eye. So because in hand-eye, we also do registration, but here we don't want to, figure out the 6th degree of freedom between two LiDAR frames. We actually just need the translation. So compared to the 4th method, we get rid of the land marking detection, which is trying to indicate the vehicle front or forward direction. But here, with the registration, we can get the translation vector between the two scans, which also indicate the vehicle motion. It's a relative motion. But anyway, because we just need to deal with the direction, then the signs it's okay whether it's positive or negative. Anyway, so by doing registration, we get this vehicle motion vector in LiDAR coordinate system, which replace the land marking direction. But again, we still need to reuse the ground normal vector to indicate the z direction of the vehicle. Then with these two, we can still continue the calculation to determine the LiDAR to vehicle transform. And here I want to mention a little bit more. So we test different registration methods, including GICP, including LOM, different methods. But here in this particular method, we use the feature descriptor we come up with to try to capture the geometry and also some property of each individual object. So this is not at the point level, this is at the object level. So it's a little bit higher level of features we extract from the scene. So for the suitable scenarios, again, this requires real-line driving because the 4th and the 5th actually follow the exact same philosophy. And for the limitation, sensor quality definitely, again, plays an important role. And again, the feature availability plays an important role. So with that, I will go to next few slides to show a little bit more details about the aggregation-based and also hand-eye based. So actually, this is from the paper that I'm going to discuss in the next session. But here, the main thing I just want to show here is the video. Maybe let me play it again. So this shows how we accumulate different scans and do the aggregation. And after that, we detect the targets, which is the traffic sign in this particular example. And all these are indicated by the white points here. So let me just quickly play it again. Yeah, so you can see gradually we get denser and denser point cloud with the aggregation. And at the end, once we kind of build a HD map in the environment, then we have an algorithm to detect each target. And here the comparison again is between accurate extrinsic and inaccurate extrinsic. The bottom one is the aggregation results with some error. So you can see all those targets has a little bit shift or the fuzziness in the 3D space. So this is the way how we do the optimization. And then comes to the left, this is our loss function we defined. Actually, it's not that complicated. So basically, since I mentioned all of them are with the rectangle board shape, we can easily use the PCA to define the 3-dimensional variance of each object and use that to formulate this loss function. So we try to minimize the variance on all 3Ds. And then in the table, we did a comparison with two state-of-art. One is the hand-eye based plus the LOM registration method. The other is ringcalibre, is also another hand-eye based method. So we can see for the orientation, basically we achieved almost the same accuracy, which is about 0.2 degree error. But we do show a better performance on the translation. Then let me move on. So this is our second method. As I mentioned, so this is extension to the previous one, which we try to generalize the target we are using. So again, here on the top right figure shows the scenario. So when the vehicle is doing a turning, then we start to trigger this calibration. So we have a region of interest which is predefined. So it's kind of in the intersection zone. So in that region, we basically extract any targets using the different method like clustering or the filtering on the space in the space. So all of them can check different targets, and we don't need to necessarily detect all of them like are they traffic light or light pole or traffic sign? We don't care. Basically, we treat them as general objects. So as you can see in the figure at the bottom, basically gives the example. There are some traffic signs as well, but they are with a certain ground surface underneath each target, and also there are some light poles on the side. So these are not covered in the previous method. And then with this target detection, we come up with a new loss function, which is based on the distance of the between the points in the neighbor in the 3D space. This actually formulate the density in terms of distance of the aggregated target. Then we try to maximize the density to do the optimization and finally determine the extrinsic parameters. And then again, in the table just gives another 2 examples of this algorithm performance. So roll pitch here is roughly 0.1 degree, slightly better than the previous one. And then hand-eye, we also tried, a different hand-eye method. There are some existing methods we direct tried, for example, in the one is GICP, we tried for the registration, which is widely used, but actually in our evaluation doesn't perform very well during especially during the turning maneuvers. And the other is from the LOM, which is the LiDAR, odometry, and mapping method. They have a specific feature defined. One is the edge feature, which shows some, which is representing some point at not on the plane. And the other is actually the planar points. So with 2 types of features, they formulate 2 different distance calculation. And then in the loss function, when they do registration, they will do basically edge to edge and plane to plane to do the optimization. We tried both. So LOM actually works better with respect to the accuracy. And then because we evaluate different sensors for the LOM was developed based on Velodyne, which is spinning mode sensor. So you can imagine there are a lot of beams. So one beam will generate one scan line, which is more like a horizontal ring. And all this feature definition is based on that kind of scanning mode. But in our study, actually, we evaluate different sensor types, which doesn't have the horizontal scan ring. Then we cannot use the LOM's feature. So we have to define our own features. So in the figure on the right, basically shows our planar feature definition. So we don't use each scan lines. Instead, we use all the points in the single frame, and then we calculate the normal vector based on a local patch of the point cloud. And with all this normal vector, basically they indicate the surface orientation, and then we can do a clustering on the normal vector space. So you can imagine if it's a wall, like a lot of points on the same plane, then all this normal vector should have the consistency. Then when you do clustering in the normal space, you can identify all those points. And then this creates a group. So this group basically belongs to the same plane. So the results basically showing here is, you can see I used 3 different colors. One is green and the other is red, and the third one is orange. So they basically representing 3 different groups based on the normal vector directions. So the orange one is the ground, which all those normal vectors are facing towards the up direction. And then the red and the green actually representing 2 other planes, normal vector directions. They are vertical walls of the buildings. So with all this, we can still extract planar features, even without a beam-based scan line. And actually, we don't do edge features. We just use the planar features. Actually, it also generate very good results. So this is our hand-eye based method. And again, in the table, I'm giving 2 examples. Roughly, the arrow, especially the orientation arrow, is also around like 0.2 degree, which is similar to what we had before. So with that, I will use this as my last slide for this keynote speech. Basically, we reviewed in the literature a lot of different LiDAR to vehicle alignment method, and all of them actually are online-based method. And then based on that, we define our own solutions. There are multiple, and there's no which one is best. They all, as I showed earlier, they all have their own limitations, and also they have their own advantages based on different conditions. So for road targets, it's very small footprint. So the detection and also the calculation, we don't use a lot of deep learning based method. So we try to minimize our computational resource for the vehicle in-vehicle implementation. So that's one advantage. So all of them are actually lightweighted. And then for scene aggregation, it's very general. We don't use specific targets. And then for hand-eye, it's very sensitive to sensor quality, but at the same time, it has a very good compatibility with the localization, because you can do X and B optimization together, instead of just calculate X. And then for the ground and the registration, we don't need a GPS. So that's one big advantage of that. So the other thing is the sensitivity analysis. I probably will cover more for that in my next talk. But the overall idea is this is an analytical study, try to derive the degeneracy condition, which I mentioned earlier, the turning and the straight line driving. They are two different scenarios, which give you different degree of freedom. So all this actually concludes our work in the past few years, actually, in GM, to cover this area, the LiDAR to vehicle alignment problem. Yeah, that's all. Yeah, thank you.
See, do you want to join?
Yeah.
Any questions from audience? I have a couple questions.
Yep.
One is a high-level question. And Xing, you mentioned about sensing multiple sensors actually, and how many sensors are right now in GM you guys are sensing, and like LiDAR, radar, camera,
Yes.
GPS, MU, and are you integrating everything together right now?
This depends on different features. So all autonomous driving features are actually, even for autonomous driving features, in terms of the parking, unparking, or highway driving, local driving, we target detection, traffic sign detection, or landmark detection, we use different combination of sensors.
And what about the computation right now? How many GPUs are in your guys' car? If that is not secret.
Actually,
that's
we don't know yet. Yeah, that's a good question.
That's not.
We are mainly for the algo development. So they are, target team actually, which basically means the in-vehicle implementation team. They are responsible for the, optimization, the system architecture, hardware, all those things. Actually, we are not so familiar with that area. So
okay.
Yeah,
and that is high-level question, and some low-level question. And Yao, you mentioned about using the ground as for the alignment.
Yeah.
You mentioned about landmarks, and what landmarks are you using on the ground, and what are the specific good landmarks or what are bad landmarks?
Yeah, actually, I was referring to the landmarking only. Yeah, landmarking only. Regularly we have like either dash line or solid line landmarkings. These are the main targets we are using currently. Yeah.
Also, another one is in your last one, and you mentioned about using the vector from the plane for the registration.
Yeah.
And I can imagine that if, for example, for the sensing, if the sensing are very close, that works super well, and like ICP. But if they are very far away, let's say I can imagine one set of planes, they could share the same vector in that case, if they are very far away from each other, would that still work well?
That will be a challenge, first of all, in general. So that's also the other test I mentioned. So when we test GICP, it doesn't do very well during turning like a frame to frame over time, over 2 timestamps. But actually, when we test GICP on 2 different sensors, which happen at the exact same time, they actually do much better. Then it comes back to this method. We know this is general problem, but actually during our test, it performed much better. I mean, compared to GICP, it actually can deal with the turnings without, sampling rate, which meet our requirements. So that's one results we found. Yeah, but in general, I agree with you. So the bigger, discrepancy between the 2 point cloud, the more difficult, for the matching. Yes.
Another question from the audience? Yeah, actually, I would like to emphasize one thing, that is, Xinyu and Yao are representing GM to give us a talk. Actually, they prepare quite a lot of slides, but GM has secret club policies, and they already tried their best to give us the details in their presentation. Actually, it's not just their own work, it's really representing quite a big department and in GM. And with that, actually, the next talk is still together with them. And actually, this is keynote talk representing GM, and they also have another effort to show some details in their one of the paper. And they have the paper. It's already here. Online LiDAR and vertical alignment using lane marking and traffic signs. And I would like to give you the further details in their research.
Okay. Yeah. Thank you. Thank you, Guoyu. Yeah, so as I mentioned, so this is a standalone topic, which is already covered. We covered some of the high level concept in the previous talk. This is merely about the first algorithm in that table we listed. We started from this one for all the work, and this is based on mainly on the traffic sign and the lane markings. And this slide probably I will do a very quick overview because Xinyu already talked about most of them. So again, the problem is trying to determine the transform between 2 coordinates. One is LiDAR, the other is vehicle. Then related work, we have hand-eye based, we have aggregation based, and particularly for this paper's work, it's under the aggregation based category. And on the right, I just show some examples. So you can see this is the LiDAR point cloud in the real world. Most of them actually for these 2 types of targets, we can extract them using the intensity, which is a reflection of the LiDAR laser beam. So both lane marking and traffic sign has higher reflection. So this actually is a very good indicator when we detect the targets. So this is a sensitivity analysis I was talking about. So degeneracy condition. And this degeneracy is mainly on the vehicle maneuver. So let me first give the conclusion at the end, which I also put here on the right bottom. So the conclusion is we consider 2 trajectories of the vehicle. One is straight line driving, the other is turning. These are the 2 most general cases. Okay, all right, thanks. Yeah. So our conclusion is for straight line driving, we can determine only 2 degrees of freedom of intrinsics. One is yaw, the other is either roll or pitch. I will explain that later. Then for turnings, it's much better. You have more excitation. You can do 5 degrees of freedom. The only thing you cannot do is the Z direction, the TZ. As I mentioned, it's because of its planar motion. Then come back to the mathematics. It doesn't seem very intuitive, but let me just give you a very high level concept. So on the top, I put some definitions. So we have the points in the LiDAR, which is the raw data from represented in the LiDAR coordinate system, which is a PLI here at the time step I. Then PI is the same point in the real world coordinate system. So basically we do 2 steps of transform. The first step from LiDAR coordinate to vehicle coordinate, and the second step from vehicle coordinate to world coordinate. So with these 2 steps, basically we map all the LiDAR points into a unique world coordinate system. And then with this calculation or definition, then we can do some sensitivity analysis. Basically, we introduce certain errors in the extrinsic to see in the final word coordinate system how the target is position is changing or a single point is changing. This basically represents the shift due to the extrinsic error. So the first test we did is actually on the left bottom. So this is a study for the translation error. So we introduced the T delta, which is the translation error in 3 dimension XYZ. And then we get the P delta I minus P delta J, which represent the target shift between timestamp I and timestamp J in the word coordinate. So it's a complicated equation, but here I just want to highlight some of the key variables. First, if you look at the right, you can see the delta X, delta Y. So these are the injected fault in the extrinsic alignment. And the thing is, you don't see delta Z, which means the delta Z is the error of the Z direction extrinsic error. It doesn't contribute to the target shift. So that's why under the planar motion, you can never observe the translation error in Z direction. You cannot use that. You cannot use the target shift to calibrate Z direction. Then on the left, in the sine function, this alpha Z minus alpha, alpha ZI minus alpha ZJ. This item basically represents the vehicle heading angle change. So if it's a straight line driving, then this will be 0 because alpha ZI will equal to alpha ZJ. So it will be 0. And then the whole, the whole equation will equal to 0 because sine 0 is 0. Then you won't be able to see the target shift. So then again, that means it would be better to have more turnings. Just like a U-turn is 180 degree. That's even better. So the bigger turnings, the better to represent the arrows by the target shift in the word coordinate. So that's one test. And then on the right, the similar test, but this is on rotation, and we separate into 3 parameters, row, pitch, yaw, independently. So the first is based on row, and again we derive this based on serial line driving. So the thing is, if we look at in the matrix, the AJ minus AI basically represent the vehicle travel distance. So if it's a straight line driving, you definitely will have some value. It's positive value. But the thing is, it will times like a sine beta Y or sine beta Z. So sine beta Y basically is the extrinsic pitch. So in our case, it's almost 0. So basically you can ignore that part. Then the sine beta Z is the yaw, the extrinsic yaw angle between the light and the vehicle. So this will be different from different applications. So in our application, beta Z is almost 90 degree. So sine beta Z will equals to 1. So basically that item will not be 0 during the straight line driving, which means you could calibrate row angle during the straight line driving. Then battery time. Then the second equation shows the exact opposite way of the pitch contribution to that target shift. And here you can see it's cosine beta Z. Because, yeah, as I mentioned, right now beta Z is almost 90 degrees. So cosine beta Z will be close to 0. So the pitch contribution will be almost 0 at the end. So that's why you cannot calibrate pitch in our case. But if you have different setup, for example, you have beta Z equal to 0 degree, then the conclusion will be flipped. You can calculate the pitch, but you cannot calculate the row. Or the other way, if you have beta Z equal to 45 degree, then you can calibrate both. But they are correlated. You still cannot determine exactly which one is which, but you may get some optimization on both. But again, anyway, it's 2 degrees of freedom. So the last one is yaw. So the good thing is you have the BI minus BJ and AI minus AJ. This represents the vehicle motion, the vehicle travel distance in the longitude direction, which is A, or on the latitude direction, which is B. So the good thing is no matter it's turning or straight line driving, you will always have A greater than 0. If it's turning, then B will also be greater than 0. That's even better. But under either case, the whole difference is not zero. So that means the target shift is observable. So that's basically a very high level summary of the analytical study. We have more detailed, but here, due to the time limit, I probably will skip that. And then comes to the algorithm architecture. On the left shows a very high level flow chart. So first step, we load all this data. We need the LiDAR data, and at the same time, we need the GPS and MU data to do the vehicle to world mapping. And then we check the enabling condition. And here, this enabling condition basically means the vehicle maneuver that I mentioned earlier, whether it's turning or whether it's a straight line driving. So based on this too, we will define two different optimization tasks. One is 5 degrees of freedom, which we call it 5P. The other is 2 degrees of freedom, we call it 2P. Then with all this data collected, we perform the aggregation based on our initial guess. So we have the extrinsic initial guess. And in the aggregated point cloud, we detect lane markings and traffic signs for each. And we will separate those targets under different enabling conditions. If it's a straight line driving, it will go to 2P optimization. Otherwise, it will go to 5P optimization. And after we run the optimization, basically we determine the row PCR and X and Y. And we will perform another standalone Z calculation. Again, this is based on prior knowledge. So this is not part of the, the fuzziness or target shift optimization. And at the end, we'll combine all of them together, which gives you 6 degrees of freedom. And we will do some outlier removal and some maturation to get the final results. And then on the right, I'm giving one example of the loss function. So we mentioned earlier, so for lane marking and traffic sign, they are kind of regular shape. So you can define them as a rectangle. So you have a very clear length, width, and height. So in this 3 dimension, we can do a PCA, which is showing on the bottom figure. They show the 3 direction variance. Then we can use them to formulate, basically we use a PCA or SVD to get all 3 dimensional variance. Then we put them together for different targets. And to sum up all the loss function gives the final loss function, which is the global optimization for all the targets. We try to minimize the variance on all 3D for all the targets, which should give us the optimum extrinsic parameters. And this slide shows how we detect the targets. So first one is lane markings. So 2 steps. First, we do ground segmentation. And again, here, as I mentioned earlier, we try to avoid deep learning based, try to make it lightweight. So we use another paper's results. They actually propose a very smart way to do the ground segmentation based on only slope or elevation of the neighbor points. So we try that, actually it works very well. So that's the ground segmentation. We determine the ground points if their slope or the elevation among the neighbor points are consistent. There's no big change. Then we think they are flat, so it's a ground. Then comes to the second step is the lane marking points. So here we took one scan line, which is one beam in the LiDAR point cloud. So if we go through the azimuth angle from left to right, it's more like a scan line. Then for lane marking points, because it's high intensity, you will see this intensity jump over the azimuth angle. So then we just come up with a simple way to define a state machine to monitor the rising edge or the falling edge in terms of the intensity change. So this actually gives us a very robust lane marking detection to pick up those lane marking points in the middle, which has higher intensity. And then on the right, basically shows one example of our results. In the whole LiDAR point cloud, the red points are basically the ground segmentation results. So all the points are considered to be on the ground. And some white points in the middle, which I also circled in those yellow circles, they are the lane marking detection results. So in this one, we detect 3 lane markings on the road. And then the rest of the points, like the blue points, are some other targets on the ground, like cars or some other trees. Yeah. So one additional thing is this is purely based on one single scan. And then with this, we accumulate all these candidate points and we do aggregation using the initial guess and again the LiDAR to word transform to aggregate them into the aggregated point clouds. And then we have some predetermined ROI region to pick up the landmarking segment as one target. And we accumulate multiple landmarking segments to do the optimization. For each one, we basically calculate the PCA variance. And this slide shows the traffic sign detection. Again, it's actually very intuitive. So first thing is also the intensity, because the usually the traffic sign has a rich reflection property. So they have very high intensity. So we use that to filter out most of other points which we are not interested in. Then with the rest of the high intensity points, we do the clustering in the 3D space, which will create each object cluster. They are considered like the groups in the 3D. Each one could be a candidate of traffic signs. And then the other thing is there are a lot of outliers in the real world. So here I put one example in the second figure on the left. So these are like the trailers of big trucks. They are also the metal material has some higher intensity reflection, and somehow if we do the first step, it will be detected as traffic signs. But they are much bigger in terms of the size compared to a regular traffic sign. And also they are sometimes we can capture more than one plane, so it doesn't give us like a board shape in the whole for the whole object. So based on all this prior knowledge, actually we created some filtering rules based on PCA to get rid of those outlier detections. And then the other one is also very interesting. It's on the right. Basically shows under many circumstances, there are a lot of traffic signs that are very close to each other. We may treat them as one single object, which is not correct. So we do have a second level of clustering, try to separate those closer targets because they are not a single target. There are multiple targets very close to each other. So we actually perform multiple the second level clustering method. And also sometimes because of some noise, we may incorrectly separate one single target into multiple. So there are some rules or the outlier management method to check the distance of different small clusters and try to either combine them or just keep them separate based on certain rules. So all these are dealing with the corner cases in the real world. So after all this, again, we accumulate all these targets in a buffer for later optimization. We will accumulate not just one target, more than one target for the optimization. And this shows some results. The first table shows the landmarking results. So we done this in only, under condition of 3-line driving. So we only do 2P. Basically, in all cases, row and yaw. And here we did multiple different tests, and we do inject different arrows to test if our algorithm is robust enough. So first 3 rows shows a 0.3-degree arrow manually injected. And the next 3 rows shows the 3-degree arrow, which is bigger injection of arrows. But you can see from the results, all of them actually achieved around 0.3-degree accuracy, no matter how bad the initial guess is. So then based on this, we think it's actually very robust. And then the second table shows the traffic sign results. This is based on 5P. And TZ, basically the Z calculation is a standalone one, but we just put it here to show you the all six degree of freedom. So these are from the multiple optimization. So each row is one optimization, use more than one traffic sign targets. And from the whole recording, because the vehicle is driving at a different location, we'll start to accumulate more and more traffic signs. So we actually perform multiple optimization during the whole trip. So at the end, the average actually is around a 0.2 degree right here. Yeah, 0.2 degree arrow, which is what we summarized earlier. And then the third table, which is on the left top, is a comparison among different recordings. So here we put 3 recording results, and actually you can see they are very consistent, which shows some robustness of this particular method. And the last table actually I showed earlier is comparison between some state of art. So these two, both of them are from the hand-eye based philosophy. And we achieved almost the same accuracy level in terms of orientation, but we do achieve much better translation error. So I think that's all of this paper. Yeah, so finally the summary. We performed an analytical study on the sensitivity analysis, or you can also consider as, wait. Yeah, I think my computer probably died. Yeah. But yeah, this is the last slide. Maybe I just talk over the air. So yeah, the first thing is we summarized the sensitivity analysis based on an analytical study. So straight line driving gives you 2 degrees of freedom, and the turning gives you 5 degrees of freedom. And then we developed the lightweight target detection. We try to minimize the computational resource for landmarking detection and traffic sign detection. And third thing is we formulate our loss function as the PCA variance on 3 dimensions. This actually gives us a good indicator for the target shift of otherness in the aggregated point cloud. So yeah, I think that's almost all. And for the future, we will extend the study. Some of them I already mentioned, but the most important thing is we try to improve the accuracy and try to improve the robustness and shorten the convergence time. Yeah, that's all. Thank you.
Thank you, Dr. Hu. Any questions, audience? Quick question, maybe.
Yeah.
So you mentioned about this pitch and draw, and doesn't really contribute too much. I think this is very true for the model, for the ground robot model, and in kinetic model for the ground, and for example, UAV people working on drones. And do you think that is simple?
That will be more complicated. Yeah. So as I mentioned earlier, those analytical study mainly based on the planned motion. But as you mentioned, if it's a drone, so that assumption doesn't hold. So you can have, up and down, or, any weird, like a roller coaster kind of motion. So in that case, that will be more complicated. And some of the, I would say some of the conclusion will still hold, but it just means that you have more scenarios you have to analyze. Yeah, this still holds, but you have more flexibility or excitation. Yes.
Thank you very much, Dr. Hu. I know we are running late. Probably we have about 10 minutes break and have a shorter break, and then we can continue. Are you okay with you?
All right.
我先暂停一下这个。
我们是不是？ You can, yeah, you may.
It's preferable that then I'm in focus of the live streamer then.
You don't have to focus on the slides. It's okay, I think. Okay, cool. You can see me. Okay. Let me introduce you.
Perfect.
Okay. Let's get started with the second half session. And the first speaker in the second session is Dr. Yuriko. My pronunciation is correct?
Close enough.
Okay. Dr. Yuriko Dun, and he's an associate professor in the Department of Computer Science in Stephens Institute of Technology. And his research focuses on 3D computer vision, including geometric and semantic relationship among a 3D scene and detecting a set of images. And Dr. Dun earned his degrees in the University of Baja, California, and a master's degree and a PhD degree from the is another center for science research, scientific research, and higher education. Okay, and he joined the Department of Computer Science of the University of North Carolina as a visiting scholar in 2018. And after that, after 1 year of postdoc in the National Council of Science and Technology, and he still remains he remained to be a postdoc in UNC, University of North Carolina until 2012. After that, he was a professor in the Stephens Institute of Technology, and he has authored over 40. I think right now it should be much more than that, right? In international conferences and journals, and he's also an associate editor or other editor board on elsewhere journals for image and vision computing. And today he will give us a talk on data-driven geometric workflows for visual localization. Yeah, thank you very much, Dr.
Thanks for the introduction. Glad to be here. Got a lot of content to cover, so hopefully we get as much as we can and make things interesting. I want to talk to you about the work we have been doing on visual localization that adapts geometric methods with deep learning approaches that have been recently developed. And in particular, I want to discuss the application of these technologies to 3 basic problems in computer vision, which are 3D reconstruction from video streams, the estimation of object pose from single images, as well as applications towards augmented reality that allow us to localize observers within an indoor environment. All of these tasks have been addressed within this combination of geometric methods and learning methods in novel ways. So let's get started. For the concept of visual localization, we see a very general framework. We have some input imagery, some pixels, and we want to have a specification of the pose of the camera. So we want to go from pixels to poses. How do we get there? For a long time, the mechanisms to get from point A to B in this diagram was to use what we call now standard or classical computer vision methods, in which we first needed to model the problem, typically in geometric terms or analytical terms, and then we needed to devise some mechanisms by which we quantified some measure of consistency, either photometric or geometric. And once we have derived such a model, we went to the problem of how to find a solution that best fits that model, and that's what we call optimization. So for a long time, we had this framework of defining a good function and then trying to solve that function through an optimization framework. And this had advantages in the sense that it was a well-founded framework which had reasonable assumptions and did not require any training, any acquisition of data a priori, except maybe to validate some of your assumptions. And importantly, it was interpretable. We could ascertain quantities such as uncertainty, and we had some geometric reasoning about the problem. And all these were very good mechanisms. However, we had these limitations of generality in the sense that these methods are brittle. Some variations in the data association mechanisms, such as variations in image capture or non-existence or non-availability of surface texture, actually hinder the performance of a lot of these classical methods. And importantly, being geometric in nature, they were ill-equipped to address higher order scene understanding mechanisms or processes. And it was general that there were specific configurations where our methods would fail or for which they could not be applied because of the problem of single image 3D geometry and the sort. So we had this dichotomy. With the development of deep learning, now we have mechanisms that allow us to inject data into the problem and try to inform through examples out of the difficulties that we have previously mentioned. And the idea is more data, more examples allow us to cover the space of possible limitations that we could run in practice. And this had the advantage of being more robust in the sense that if you were able to provide examples that targeted the specific failure cases, you could make some headway on this, and you could circumvent to some degree the degeneracy of some of the classical method solutions. Moreover, we could also incorporate semantics and higher order logic into these processes, and they were done implicitly through the incorporation of supervision in the learning framework. However, the disadvantage here is that the generalization was not so good. Now we were tied to the actual data we train upon, and depending on the scope of this training data was the scope of the solutions that you could attain from these methods. Additionally, we had the challenge of interpretability, where a lot of times these methods were black boxes. By this I mean the learning-based methods were black boxes, which gave you a solution but did not elucidate the choices and the criteria that were used or the justifications for the solutions. So yes, you get some solutions, but if your data is out of sample, if your runtime instance is out of sample, it's kind of difficult to solve. So this is the dichotomy that we had. In essence, we had geometric methods, classical geometric methods that had good generalization interpretability as long as the data input to them was reliable. And we have very robust and semantically rich solutions for learning methods that were useful as long as the data was within the scope of the training data that was being used in the training. So we want to hopefully get the best of both worlds here. So how can we do that? We take this approach where we actually utilize networks to provide data association queues and use those in the modeling of our problem, or use that to feed the modeling of our problem. So hopefully for this, we take the best of both worlds and actually achieve robustness, the richness of semantics and generalization and interpretability. The argument might say that why don't we get the short end of the stick here, and why don't we get the worst scenario? Well, that is what the actual effort is in our work, trying to achieve these best case scenarios in different application domains. So the first application domain I want to discuss today is visual odometry, which is appropriate for the workshop today because this is the title of the workshop. So I'll spend a good portion of my time in this domain and asymptotically reduce the time assigned to subsequent task. So visual odometry, the task is well known in this room at least, where we want to estimate how a camera moves from a sequence of images. And the idea is to build these pose chains that can estimate the camera motion between subsequent elements and then try to build a trajectory path in the scene for the observer, which is being modeled. And in practice, methods like OrbSlam, a popular feature-based method, has these advantages that we assume the availability of robust feature detection and appearance constancy. A lot of times this is not available. And in practice, when we participated in the Tartan Air Visual Odometry Challenge, we saw that we lost track around 16% of the frames. So for visual odometry, this is not so good. So in practice, we wanted to address those challenges, that what happens when we lose tracking due to feature insufficiency or feature inconsistency. Well, then let's do deep learning based methods. We saw that they don't generalize that well. If you train on a certain data set and you test on a different one, then we end up with a performance drop that is significant and almost symmetric, depending if you have two different data sets, you flip the training, you see that disastrous behavior arises. And more importantly, in practice, these methods compared to standard classical SIF feature extraction and 5-point method for camera pose estimation, the basic framework for for visual odometry, this is in general more robust than trying to actually even use in sample evaluation exams. So we wanted to address this by combining both geometry and learning methods. So this is our first geometric workflow framework that we want to present. One where we devise visual odometry as a dense indirect estimation problem, where we want to use as input optical flow, and then based on that optical flow, define how the camera motion can be estimated. And importantly, we want to use state-of-the-art networks for optical flow estimation because there's a lot of talented people working in this domain. We just want to reap the benefits of their hard work. So if under the assumption that if we have better optical flow estimators, then we just piggyback on their achievements and get better visual odometry estimation. So how do we do this? First, we have to account for how are we going to define the mathematics of our model and how we are going to optimize that, under the assumption that our input is given by optical flow network that somebody else was gracious enough to make public. So this gave rise to our graphical model, the holistic graphical model called BOLDOR, which stands for Visual Odometry under Log Logistic Dense Optical Flow Residuals. This was a CVPR paper from back in 2020. And the idea here is we model as variables that need to be estimated our camera poses, our depth maps, and a selection mask that tells us which part of the scene is actually rigid in nature. So basically, a selection probability for the actual optical flows to participate or not in the camera pose estimation. The main concept we're following here is that of rigid flow. Basically, what part of the optical flow corresponds to the motion of a static 3D element that is induced only by the movement of the camera. That is, what part of the 2D motion field is caused exclusively by camera motion. And what we observe is actually an optical flow. And what we want to estimate is which is a rigid flow. And from that, estimate what is the pose, what is the geometry, and which is the selection of dense per pixel selection. What we leverage here is adding a specific noise model that told us that what is the behavior we expect out of our optical flow estimator. And if we can model that behavior accurately, then we can backtrack and robustly estimate what the actual rigid flow is in the scene. So hidden variables are, as we see here, our depth map, the poses, and a consistency mask, and our inputs are just a set of optical flows. Okay, our operation of our system is as this. We work on a small batch, maybe 6-7 images, and we send this to a black box optical flow estimate. And then these particular inputs are computed externally. We start with an estimate of where our depth map is, and from that we are able to make optical flow tracks, which tells us how a particular point has moved across the sequence. Turns out, if you have a depth map and you have optical flow, you have 3D to 2D correspondences, and from that you can run a plethora of different structure for motion methods. So the idea is we can compute what is the discrepancy between the observed optical flow and the hypothesis of a rigid flow. And this residual is the one that will tell us how mistaken our optical flow estimator is. So based on this residual, we can actually fit a specific error model to the optical flow and use that to update our estimates of the residuals, our estimates of the camera poses, and our estimates of the depth maps. The idea is we check the consistency of our optical flow with our current hypothesis on motion and geometry and try to refine this iteratively. In practice, this becomes a generalized EN method. We estimate one thing by fixing the other. So this error model, we observed that in practice, our optical flow estimation had an endpoint error that depended mostly on the magnitude of the optical flow. So if we can model mathematically how well or how bad the optical flow estimate is in terms of its magnitude, we can build a model for that. We went and estimated on multiple data sets and the residuals with respect to the ground truth optical flow provided in those benchmarks. And we saw that the FIST model actually provided the best fit across diverse methods and diverse data sets. This FIST model is a log logistic model, which tells us that here you see the actual empirical distributions of in gray of the actual errors with respect to the magnitude, and we see that the best fit is actually given by our FIST distribution model. Based on this particular assumption, we can say that we can pose our estimation process as our optical flow given our rigid flow and our rigid selection probabilities to be either FISC if our rigidness is set to 1, and if it's not rigid, then we say that the error is uniform. We haven't uniform prior there. So now this is the model we want to actually assign to our optical flow estimator. However, we have this challenge now that how do we perform dense estimation over the a set of images in on a per pixel basis, and how can we mitigate the non-convexity of our log logistic error model? Well, the idea here is, as I mentioned before, we end up with an iterative refinement where we actually keep one part of the components fixed and update one of them, and we iterate with the process. Basically, we have to update the rigidness based on our observations, then update the cameras, then the rigidness again, and then the depth in a cycle. To update our depth maps, we use something very similar to what's currently implemented in the state-of-the-art stereo or structural motion pipeline call map. They use a sample and propagate scheme. We use something very similar, where we basically perform directional updates and sampling to perform Monte Carlo sampling over the pixels. The advantages of assuming an error based on their fixed model gives us more localized local maximum for the depth estimation sampling. In order to estimate the rigidness maps, we use something akin to the Markov chain propagation to provide smoothness over the entire sequence and over adjacent pixels. What we see here is the input images, the optical flow associated with these images, and our estimated depth map. On the bottom right, we see the rigidness map that gets computed on a per frame basis, and we see that as we move forward, some of the components of the current frame actually leave the field of view of the camera as we are moving forward. So that's why we see an apparent shrinking of the rigidness map, only because it is defined with respect to the first frame of the sequence. But it's not implicit that we are less confident on the rigidness of things on the periphery. Something to note here: we see a dynamic object here in the foreground, and we get discrimination of that motion in the rigidness map. We see that this particular content does not comply with the rigid motion assumption with respect to the motion of the entire camera. So we are able to basically segment out dynamic components that will contaminate our motion estimation. That motion estimation is presented here. How do we estimate dense from a dense set of observations? Because now we have, for each pixel we have a track, we have a potential hypothesis for a 3D to 2D correspondence, because we already know a base depth map from which the depth was propagated. In this scenario, what we do is something similar to Ransack, where we each pixel gets an assignment of potential neighbors, which are weighted by their actual confidence in the richness map. And each one of these will generate an hypothesis in the Lie algebra. Basically, we generate for these 3 points, we run P3P, and we get an hypothesis solution that corresponds to that particular 3-point sample. Every pixel gets 3 particular or two neighbors to try to generate a hypothesis. And once we populate this space, we run mean shift on this to find what is the mode of a distribution in this Lie algebra space. The assumption here is that the location of this particular mode will correspond to the most popular or the most accurate location. In this scenario, we see that assuming that the area is Gaussian gives us a significant spread in our estimation of where the epipole would be, whereas using our FISP model actually gives us a more accurate estimation, or more localized. In practice, this means that we have smaller covariances and we get more accurate estimates. This is an example on TD. We see that on the left, we see the input, this is the imagery, this is the optical flow, and these are the depth maps, confidence maps, and on the bottom, we see the actual motion that's computed strictly from visual odometry. There's no global refinement or estimation going on there. The red is our motion estimate, the green is our visual odometry. And I'm happy to say that they look very similar. So if you cannot see the difference between them, that's good. Okay. Yes. These are some examples on the visual odometry or the SLAM challenge we participated. On the right, we see a very dark scene where it's hard to maintain feature tracking. On the right, we see an underwater simulation, and we see how our confidence maps are able to identify moving objects and inconsistent components that arise from optical aberrations. Yeah, again, these are the images, this confidence map, optical flows, and these are the trajectories we computed. We extended our visual odometry pipeline to include a backend to do loop closure and graph pose refinement. Basically, pose only bundle adjustment, if you like, or rotation averaging. In this scenario, we see the results of our method in outdoor environments and actually for platforms that are ground-based or UAVs on the right. And our system runs in real time. By that I mean about 15 frames per second, doing the entire loop of optical flow and depth estimation and pose estimation. Yeah, so we have an open source GitHub for if you're interested in exploring more of this type of framework. Okay, just to highlight that indeed our method outperformed back in the day the then state-of-the-art for monocular visual odometry and SLAM. Okay, let me see how you can still have a few minutes left. Let me let's see how am I doing here. For object localization, we want to estimate what is the pose of the camera with respect to a specific object in the scene. In particular, we want to do this for autonomous driving operation applications, where the goal is to estimate the pose of a car with respect to the camera. And this is the work that we actually are presenting in this conference. So let me discuss the details. Here we're working with NOx map estimation. The idea is normalized object coordinate system, which basically for a given image provides a dense 3D field of geometry corresponding to that image patch. Once you have that, you actually have 2D to 3D correspondences, which then you can just simply pass over to a PNP solver and get a pose. But the challenge here is, how do you generate this 3D estimation from just a single image? This is a standard mechanism, standard workflow, where we have an image, we have a network prediction of the normalized object coordinates, and then we pass it to a PNP solver, which is actually uses a thrust region solver, and then we get a camera pose at the end. We want to, this already exists, so we cannot add much to this framework. However, supervision for this network that learns what is the local geometry, that is still a challenge, and that's where we actually focus on. The idea here is, if you want to generate for a single object detection an actual 3D geometry estimate, you can use LiDAR to infer that a dense geometry. However, LiDAR is noisy and sparse, and the process of generalizing from dense samples to an actual dense knock is an open problem. Current approaches to actually densify, basically fill in the holes of the LiDAR sampling, lead, unfortunately, to aberrations in the geometry. So what we do here is try to come up with a mechanism based on neural rendering that will allow us to generate accurate shapes based on the single image input. And the idea is to replace this estimated geometry as the supervision for our learning method that generates a knock. So just to make it in diagrams, typically you rely on LiDAR to provide supervision for the methods that generate the normalized object coordinate. What we want to do is eliminate the sensor requirement and basically do an analysis at the dataset level to provide a low rank approximation for the geometry that we want to use as supervision for our knock detection. So we do this by defining canonical latent grids that basically provide the deformation of the actual shape we want to encode, and we have this be learned from the data. Basically, we then, for each input, be able to provide coefficients for how the shape and color vary across the image, and then use this encodings as the proxies to be injected into the scene in order to then be fed into a rendering engine that we will then use to generate our knocks. So this is the straightforward workflow. We have to impose some constraints. Basically, our main constraint is a silhouette constraint. We want to ensure that our geometry does not go beyond the segmentation mask that can be provided. Alternatively, we can also include the color similarity between our render output from our single image rendering, and if possible, we can use LiDAR as an additional task, additional signal if necessary. Let's see, how am I doing in time? Okay, pretty good. So keep in mind that we need to regularize the amount of flexibility that we have in our shape bases. So we want to regularize the weights that we estimate. We want them to be relatively well behaved. So by trying to associate them to a normal distribution, that helps reduce frivolous geometry being generated. Similarly, for the silhouette constraint, we impose a density prior, which allows us to have better fitting to the actual visual whole, if possible. Finally, I guess we also determined that we can focus on specific areas of the image, but we to minimize the context that gets injected into our estimation. Here we see some examples. If you try to initialize only with a LiDAR information, you get a proxy geometry that looks more or less accurate, but has a lot of variability. You can try to complete or densify your LiDAR estimation, and you still get some aberrations now on the boundaries. Our method, using just the segmentation mask as supervision, provides a fairly adequate geometry, which can be improved by using by adding the use of the regularization that imposes silhouette consistency as well as smoothing deformations. Our method attains state-of-the-art results compared to existing approaches that are based on just simple regression of the camera pose, and as well as using the CATs as a proxy for supervision. Okay, I'm just going to show you here an example of our system working online. We see on the top we see the estimated knocks by our system. On the bottom we see the detected bounding boxes in 3D, and on the right we see a bird's eye view of our estimation. Let's see. Okay, so I'll, as promised, I will go quicker the more I go to the right. The third application I want to discuss is floor plan localization. The idea is you are given an actual image and you want to estimate its 2D location with respect to a given floor plan. That is, you know, the geometry of the dwelling where you're in a bird's eye view, but you also are given an image that could be a panorama or could be a limited field of view image. The idea here is where is it and what is its orientation? That is what we're trying to determine. And to do this, we basically adopt a Monte Carlo approach where these methods try to enforce a model of depth consistency and do some sampling to get which is the position that is more consistent with the depths we observe, and use that for camera pose. We actually change this framework and try to do an image and environment encoding mechanism that will put the representation of a sample in the scene in a sample image into the same metric space where we can actually compute a similarity between them. So in this case, our framework is replacing the entire process. As I said before, our goal is to devise, learn an actual network that is able to encode the images, whether they be panoramas or perspective images, as well as sample locations in the environment into the same representation space, and then try to find nearest neighbors in this particular environment. This heat map basically says if we were to sample very, very densely, what would be our overall distribution of likelihoods for similarity with respect to a given image. So for the image branch, we basically divide the image into particular column regions. Interestingly, our contribution here was that we provide a description that is cyclical in nature. That is, by a circular histogram, now we can actually have a directional component to each one of these particular columns. In the image actually has a sector in the circle that can actually be manipulated. Importantly, we can model both panoramas and perspective images in a very straightforward manner, only that these are partial samples. Well, the next concept here is that our framework, by relying only on a point net network to process the raster of the floor plan, is limited in its expressibility, because every camera location will sample points based only on visibility, and this will give a very ambiguous likelihood, because all the points in the same room more or less see the same points, with some variation, but if visibility is the only test, that turns out to be insufficient. Our solution is to do overdetermined or redundant representations, where we actually learn, instead of a single representation for a point, we build a dictionary, which we actually have to query, and depending on the viewing parameters with respect to the camera, they are selected adaptively. Basically, we assign different weights depending on the distance and the angles to these particular components. And this actually provides very well localized post estimates. That is, we can actually identify global maximum in a very reliable way. We sample the entire image, the entire floor plan very efficiently to a rate of 10,000 kilohertz. So that is very efficient. And we perform single 1D alignment between our image representation and our map sample representation. And this obviates sampling over the spatial rotations by doing some pre-processing alignment. Let me give you some quick example. We also had a mechanism to refine, to eliminate the quantization given by our sampling. And our training is based on a triplet loss, basically saying that we need to have our locations and the ground truth be very close in presentation space. And here are some examples of how the localization evolves with respect to the angle of view, field of view, the horizontal field of view. We see that for very narrow images, there's a lot of ambiguity, multiple local minimum, but as we expand the field of view to a reasonable angle, we get localized location. Okay. So let me just very quickly mention that this works with perspective images as well as panoramas. Our code book, yeah, sorry, I didn't have my presenter view too. So to skip over this content. Importantly, our method allows for the interpretation of a given descriptor. Now, since our features depend on the orientation and distance to the scene, turns out that we can invert the process of encoding to actually interpret what the geometry is. And we can build rough approximations of the environment surrounding a viewpoint from our descriptor. However, it's important to highlight that our method has high variability, and given the codebook representation, every room gets its own discriminating feature space. Going forward, we wanted to generalize this to 3D, and this is what we are currently working on how to actually model how viewpoints depend on a sample data set. Just very quickly, let me show you that we have technology now that is able to differentiate between an image that is rotated based on the content of the rays that actually encompass all the pixels that it generates. Why would we want to do this? Turns out that we can actually learn how capture on this is captures from ScanNet. If we are given a new environment, can we predict, based on the previous observations, where the camera will be most likely placed in previously unseen environment? And this is the type of work we're trying to get going now, and we have preliminary results that have been included in the ECCV, I think. Let me just very quickly just show you that for a given environment, we sample which are the most likely locations in a manner analogous to what I described before for 2D. Now we're doing this in 3D. We want to know for an environment, where is the camera most likely to be, and in order to inform this for viewpoint planning tasks. Importantly, we can impose semantic constraints to this. Basically, we see that our selected viewpoints or the local maximum of a distribution is actually concordant with the actual samples that have been held out. And we can even impose, if our training data has focus on a specific object, then, and you use that to train our model, we will only capture images following that behavior. So we are very optimistic about these results. Okay, let me just quickly end it here by saying that all this work was a part of one very laborious PhD student, and I recommend that if you're interested in the most recent work on the object localization based on neural rendering, this work will be presented in this conference, and Dr. Sheshang Ming was the author of the majority of these efforts here. Thanks a lot, and I open it for questions.
I will quick time for 1-2 questions.
Yeah.
Okay. Probably I have a question.
Yes, yes.
In the polynomial image and for the floor plan localization,
Hmm.
and once you segment the images into different components, it looks like for each component, the distortion is actually not as much as the whole image. Actually, that is pretty close to the perspective image looks like.
Mhm.
Have you compared with perspective image localization with the polynomial image localization in research?
Yeah, in practice, we see that the bigger the field of view of our camera, the more information we gather, and the more ambiguities we can resolve. At the end, we are modeling our features based on circular histograms, and the aggregation is surprisingly robust. Let me see here the actual too many clicks. Yeah, well, this is the example. Here we try, we compare against different fields of view, and the best results are attained when we get the maximum field of view. Yes, panoramas are quantitatively easier to register or to align to the model, but the narrow field of view does provide a reasonable estimation. Yeah, but more pixels are better for this.
Thank you very much.
Thank you. Okay.
Share screen，然后 share 一下你的 screen 再送到。
Okay, sorry. Share screen. Yeah. Yeah. Okay, cool.
Well, it's our great pleasure to have Dr. Yanxi Liu to give us the keynote talk. And he's currently a full professor in Penn State University. And he has background in physics, computer science, and theoretical robotics and AI. And with NSF research fellowship, education fellowship work, she spent 1 year at NSF Center for Discrete Mathematics and Theoretical Computer Science before joining the faculty of Robotics Institute in Carnegie Mellon University, which is for 10 years. And after Carnegie Mellon University's tenure, and she's currently the director of the Human Motion Capture Lab for the Smart Health and co-directs the lab for the perception and action and cognition lab. And she has quite a lot of research in the computational regularity, which is funded by NSF National Science Foundation, including a INSPIRE grant, and with diverse applications in robotics, human machine perception, and human health. Her industry visit resulted in 2 granted patents on applying the computation symmetry to urban scenes. And she has led 3 international competitions in computer vision algorithm for detecting symmetrics in the world, and which is in ICCV 2017, CVPR 2013, and CVPR 2011. And she served as a co-program chair for CVPR 2017 and WACV in 2019, and area chair for multiple conferences in CVPR, ECCV, ICCV, MICAI. And she's also an associate editor for the journal PAMI, which is the best journal in the entire computer science area. And let's welcome Dr. Liu for her talk.
Thank you for the introduction. And thank you for being here. Outside is so attractive. And you can still remain. Let me start the timer. So I'm going to give a talk, which perhaps rather non-mainstream, first of all. And secondly, perhaps basically trendy, okay? So I'm going to go back to history, first of all, and I'm going to try to convince you about something perhaps no one, as far as I can tell, in this conference for the past N years that ever talked about. And it's kind of interesting because it relates to my root training. So I would rephrase this in this way as well. For those who know me, perhaps you know I'm just pathologically addicted to group theory. But let me talk about, thank you for the invitation once again. And this is a very good workshop in the sense that it's really addressing something everybody cares about. So this is very interesting, useful. And when I prepared this talk, I start to, because of my own training from robotics to computer vision, computer graphics, medicine, some kind of medical applications, I start to realize how broadly the issues addressed here can be applied. Recently, we have done quite a bit of things with humanoid robotics, including a new course for undergrads. And from my previous and current duties, sometimes at the NIH to review, lots of these people propose all kinds of new technology to do like this kind of surgery, but everything related to localization. And of course, in every kind of media, right? Could be on the road, in the air, under the water. I don't know what the lower left is, on top of some, what is it? Oh, okay. Okay, thanks. Yeah, so it's really versatile. But I want to draw your attention or trying to push you to focus on something that perhaps less being specified before in an abstract way. That is, when you decide where things are, either where you are or where something is, can we consider this in the context of having a contact that is physically touching something, then trying to determine where things are. So I give you a very simple example, a block on the planar surface. So in robotics, this actually, even robot itself, maybe it's a very common question, is that where I am with respect to something else, world coordinate system or solid 1 versus solid 2, etc. So if we want to formalize this, so next picture, a little bit messy. We can start to think, I'm sure everyone here is trained for talking about coordinate systems. You can have a world, and you can have something established on the object, and something we sometimes use the word feature or surface, whatever, is this cube, for example, it has 6 surfaces. And when we talk about features, we could talk about each of the planes. Therefore, for convenience, when we coding or when we formalize things, we can do a local coordinates. That's why you see this thing on my slide, right? So when you decide the relative location of the two things under the constraint that they have to have a surface contact, you actually can write this out geometrically, symbolically. Actually, symbolically, something like this. Okay, relative location of two objects. Now, the thing can become a little bit more interesting is this. First, you have this object have one contact, and then suppose you specify this object has to go along the table and along the wall, like object B here. And then the third one, you can say, oh, not only that wall, you have to be along the other wall as well. And here you basically can see with the increasing of the constraints, the location, the relative location changes. But also another thing I want to point out is that, so the degree of freedom is different. That is, location doesn't mean a single place or orientation. It actually can change. In some times, in a continuous way, for example, object B can be sliding along the wall and the surface of the table, or object C. Okay, so here is one thing. If you care about, in the abstract sense of object's shape, if it's a real cube, it actually has multiple ways of being positioned there, if consider each surface of it being equivalent. So this actually forming something really interesting, and you can formalize using, here I wrote down without explaining what those capital G's are. Those are symmetry groups of the contacting surface. So give you a little bit of history. So this paper from long ago is in French. Was quite actually enlightening. So later I learned a little bit French and able to read this. But the point is this person basically using all this group theoretical stuff to figure out all kinds of mechanisms when they have under contact, just like joints. I mean, think about yourself, right? The reason you are being a human, you actually have lots of joints. Humanoid robots and humans share the same kind of thing. So mechanism, or in this case, group theory and mechanism, turns out to be a very general topic. And this person in particular proposed a way to categorize and represent those linkages. And just to once again put myself in the picture as well, because I'm actually following this kind of thing for multiple years. I think for some of you, maybe, I'm not sure, some young students may not even be born then, is that we actually made the initial formalization computable. So basically my thesis was on computation of using group theory in robotics assembly planning. In any case, you may wonder, I'm going to talk about symmetry first. You may wonder what's symmetry to do with anything that we're talking about here. I don't know if you ever looked into the definition of a symmetry, and later on I want to go into the group theory part. So symmetry by definition mathematically, actually it's pretty surprising at the time when it came out, because it's a modern way to talk about shapes. Before, when we talk about, oh, there's a square, there's a circle, but if you want to talk in a mathematical way, it's actually meaning whatever that shape is, how it remains to be invariant, shape-wise invariant, or set-wise invariant under what kind of transformation. So actually, symmetry by definition is a transformation. Now, you guys should all appreciate in robotics, people actually have transformation groups in a sense, not English group, but the mathematical groups. And I think some of the researchers in computer vision CVPR community also study things using like projective geometry, Lie group, and all that stuff. So that's how it relates. And I'm going to just quickly go through this, but I'm not going to teach. It is an algebraic structure. A Greek property is it has an enclosure property. It basically means two operations operate on your whatever group, it remains to be in the group. So the reason symmetry is relevant is that, remember, if you see, I mean, even a face reflection or a circle rotating around, all those symmetries individually, they actually form a group. The binary operation, since we are all doing this kind of business, so you can think of the operation transformation represented by matrix. So the operation is a matrix multiplication. So it's a composition. Okay, so back to things in contact. It's quite actually comforting in some sense and educational that to learn our previous researchers and engineers have actually generalized all possible surface contact. That means I have object, I touch another object. Actually, there is a little area they share in common. That's called the surface contact. And turns out there are only 6 of those, no more. Okay, and each of them corresponding to a specific kind of relative motion. This is another drawing by actually Matt Mason, used to be my colleague at CMU. Very nice research on fine motion planning that from his paper. But in any case, but that's not the limit. So you can have, so I should also bring a sphere, but doesn't matter. So this kind of contact, of course, you can have point or edge contact as well. Therefore, the kinds of so-called joints is actually include all kinds of things that can be in contact. And the group theory or symmetry groups of the contacting surface actually can be characterized very nicely. So this is under some specific XYZ convenient coordinate system. So you can see identity has nothing. And then the bottom one is Euclidean group, proper Euclidean group, because in robotics, usually people don't deal with reflections because robot can't reflect anything. Therefore, you can see the translations, rotations, and along the 3 axes. And even more interesting is all this group actually forming a hierarchy from the very big group, and they have subgroups, and then they all actually are parents of the identity group. And actually the part I happens to be in this figure is red is that furthermore, I did work, especially at Carnegie Mellon on visual symmetry groups. But here is the whole picture. If you have absorbed some of the things I have talked about before, is that here basically not just about surface contact, but if you just have a contact between any 2 objects, and let's just say the contact surface can be characterized by some kind of algebra expression, then you have associated group. G1, G2 are the symmetry groups of those respective ones. But the cool thing is, if they have area contact, that means lower pairs, G1 equals G2. So they can also further constrained. So yeah, let me stay here. So lots of work has been done, but I'm going to just summarize that. First of all, we can formalize them object contact this way. Secondly, we can prove, okay, this is the difference between heuristics and something you can prove. We can actually prove all the surface contact can be expressed as the intersection of those surface symmetry groups, surface feature symmetry groups. And then, of course, as computer scientists, we actually have to compute this. So my thesis devoted most of it trying to figure out the efficient way to do this. And the intersection of the groups basically mapped from algebra to geometry. And then at the geometry domain, just do some intersection, I mean, all kinds of geometry computations, ultimately figure out what's the result. So this has been done. And then ultimately, it's a long time ago, but we have done task level planning. Basically, you tell robot to say, hey, you go to IKEA, get a bunch of stuff and say, put them together, but without saying exactly how. But if the robot has the CAD model of the things and using this kind of geometric reasoning, group theory, and analyze all the symmetry groups, mating features, and they can figure this out. And then output a plan at the bottom to a robot to assemble it. And of course, assembly ordering also very important. In any case, so this is something that has been done and tried out. But what's interesting here is that what we have learned, all contexts can be represented this way. And secondly, multiple contexts can be expressed this way. And the relative location of things in contact actually can be represented as the intersections of the groups. But during this study, we also noticed that if you only talk about math, sometimes seemingly it is rather strange, right? You can say this two thing has surface contact because when we talk about surface, algebraic surface is infinitely large. Therefore, I remember at the time, lots of roboticists basically coding this is so ambiguous, you can't really specify using groups because they're so general and using algebra. But on the other hand, this actually exactly when you specify surface contact, one single surface contact meant. And this is also ultimately inspired us to transfer this whole idea of assembly planning using physical contact to vision-based relative location using visual cues. But just as a textbook kind of explanation. So of course, in our, like, you must have to learn basics 101 computer vision, we talk about projected geometry and all this stuff. And when we talk about this, of course, we don't have a surface contact with something, but we have this virtual or imaginary, or for those of you who nowadays start to get into the AR, VR field, you would understand that, yeah, we have actually lots of things not physically there, but geometrically there, or in the model or in a virtual way that can feel as if it's real. So that's exact idea. Whatever we have developed before, which are inferring location, relative locations by physical context. Actually, we ultimately can do this as a chain, mechanical chain, basically thinking about like a robotic hand gripper, right? So this is all very common actually in robotics. But here for computer vision people or for visual sensors, we could use those planes, imaginary planes, or even sometimes the kind of sweeping things that has a curved frontal surface. Those kind of things can be abstracted into surfaces, algebraic surface, in contact. So ultimately, we may want to figure out how those things have relative motion, and if we use this kind of method to represent primitive features, they are virtual, they are not real, not physical, but can be represented as such. We can use all the mathematical kind of reasoning and the proven results into this. And just to go one the case like what we have dealt before, this is not surface contact, of course. This is line contact. But this actually also has a little trick that is when you deal with algebra, you can always find in some short paths trying to be able to take out common terms. But what I'm trying to put this example here just to give you an analogy that if you think of what I just talked about before, we can think of in a kind of analogy way that we have dealt with the physical context of planes with objects, in this case is a cylinder, but with your visual plane, virtual plane with object in the world. In any case, so this basically gave us a way to infer relative motion. I just want to, before I go to application of this, just to mention that this kind of group theoretical computational making computational methods from group theory all the way to your real data has been applied actually in my own research in many different fields. And in particular on the top left, kind of relevant to this workshop topic is that when we observe human motion, walking in particular, we have, biologically built way of doing things. So we actually you can put a camera anywhere to look at this person, right? But the interesting thing is, if we look at a dog or a horse or some kind of animal, they also can have a gait. And just by analyzing how the legs changing. We do left, right, left, right. But when a dog or horse, when they really galloping, they actually don't have this bilateral alternative. So the interesting is from very low res video, we actually can extract that kind of change variation along the time axis, and using some very simple method. Just we actually collect data when we're CMU had in a room multiple cameras, people on treadmill, but we use a very simple representation, basically just get the silhouette of whatever is motion and then project to the X and the Y direction, and then build a pattern on the right. So basically one is projecting to X-axis, one is projecting to Y. And you can see the motion, but more importantly, if you look at this person when it's having a gait from different angles, those patterns appear completely different. And just so happened, if you turn to group theory, this kind of pattern called a freeze pattern, meaning changing along one dimension. In this case, the dimension is the time, right? There are only 7 provable, possible 7 cases. And using that, you actually can tell which angle you're looking at this person. So so these are the 7. And this not only would be useful for indoor cases, actually outdoor as well. In any case, what we have done, carried over from this kind of solid physical context to now we can deal with more current modern technology. For example, in this case of, I'm just showing you briefly of a app we have actually developed. What has been said, I am actually doing motion capture of human activities of all kinds. So we actually built this app. Of course, when you capture the person doing, in this case, a Tai Chi, is doing things on the ground. So it's a planar surface. But when you're trying to play this in your app, you actually want to make, it's almost like assembly, okay? It's like you want this person forming some kind of plane, and you have a real plane from your phone camera, and you want this to have assembled, have a lower pair planar joint contact. So you will have actually the person from the far, the shorter guy is a real guy, is in my motion capture lab, and the person closer is actually the master, but we animated in the app. So this is in my kitchen, and this is on one of my pianos. So yeah. So ignore some of the artifacts. This is a very early version, so there are trees in the air, but the thing I want you to see is whether this woman is on the ground. Okay. So this is really, I just did a video when we motion capture the male character here. And the reason, the technique behind it actually is still kind of visual based, because we're actually trying to find the features on the ground. But instead of treating it just as individual point clouds and everything, we're actually treating it as a planar surface, or trying to fit one. So in some sense, we're just overcoming some of the noisy data and going for the more, I think in some sense, the previous talk kind of hinted that is more kind of higher level structure for the matching. But of course, whatever I've talked about using group theoretical way to do this contact-based relative location inference, is that's all in the background. But as application here is there's all those has been said and done, and the ultimate goal is to make it visually believable. Okay, moving on. So the question about localization, I think it's actually kind of interesting, very useful and interesting question, because I'm sure we all had a sense of get lost at some point in our life. And when you think about it, when you get lost, of course, yeah, sometimes you just get to a new place. You really don't know where's where. But oftentimes it's also like the example of this maze is that things look similar in all directions or in two directions or in whatever, is because once again, I'm going to be coming back to the concept of symmetry. The symmetry can help you, the group theory can help you, but can also if you don't address it, it actually can damage your application. So in Chinese, we have this word basically meaning water can get the boat float, but it can also sink the boat. So although I'm definitely a firm promoter of using formal methods and making it computationally feasible. However, we should all not ignore the difficulties. I think the difference, like I mentioned before, is between heuristic and having something, first of all, complete. Group theory actually completely captures the kind of context that we care about, and unambiguous. So this is another situation. People think group theory is ambiguous because when you have a symmetry group, say fourfold rotation, that means this thing can do this way, this way, this way, this way. So which way is it? But if it is symmetrical, that means all those ways are equally likely. So that's not ambiguous, that is completeness. But this kind of thing require either someone trained in both very mathematically rigorously and computationally very hands-on, or collaboration between different fields. And I think that's really something we should go for to get things, instead of just going, everybody just say, oh, let's get the data, collect data, let's just do something, without truly understand what's that essence, that little skeleton in the data that mathematically well justified. I think that's my talk. Thanks.
Any question from the audience? Okay, actually, I can see it's very interesting. It's really Dr. Liu's style. Quite a lot of mathematics and theoretical things compared with my other talks. I really enjoy that. And one thing I would like to ask for my own research, for example, we sometimes need to use grapher, ARM grapher to do the automatic harvesting for the agriculture people, and sometimes they do need to do the localization, actually using the grapher to localize the arm, localize where the fruit is. And so even for the medical research, some surgery robotics need to do some exact localization about their arm as well. So that kind of shape is relatively compact compared with the surface you have shown demo with. And do you think that is theoretically that is makes quite a lot optimization and the computation more complicated, that is not easy to solve, or you think that is more or less the same as the demo you have shown in the localization perspective?
Yeah, thanks for this question. Actually, while you're talking about this, I just want to mention there is a paper called the Grasping Symmetry. You should take a look at it. It's actually by the robotics researchers from Oxford, long time ago, but I think it's worth looking into. But what you said actually is quite interesting. Actually, I'm also becoming very interested because I have a garden now, so I'm interested in agriculture in a small scale. Yes, I think it's a general thing, right? Reality never be as clean, as perfect as math, right? You don't get a circular tomato or potato or whatever. But yes, some kind of optimization or approximation indeed is needed, especially in terms of grasping. You got to figure out where the center of mass, right? And you really want the force direction that intersect with that. Otherwise, we'll be flipping or rotating and get out of hand. So my undergrad actually is physics. So this is physics stuff, geometry, spatial reasoning, and I guess probability or uncertainty reasoning. It's all have to be combined. It's definitely not one thing, or you just do pure group theory, you win. But what I'm trying to promote is a principled way. You always have a guiding principle, and you still have to deal with noisy data, imperfect shapes, weird, whatever, sensory data, etc. It is a consort effort.
I can see once we have some theoretical build up and with some assumptions with the proximity, and I think that would be very good guidance for many of the localization, not for just for the robot, maybe for the arm, for the other medical, for robotic, for agricultural robotic, that would be very good guidance for many of those applications. Right now, I can see in my at least in my own research, I can see that it's a very big problem in accurate grasping, actually.
Thanks for confirming that.
Any other questions?
Yeah, actually, I want to see a show of hands. How many of you in your education learned group theory? 1, 2, 3. Okay. Oh, there's some more. Good. Yeah, because I'm actually trying to teach like a combination of group theory with computation, because I call it computational regularity, but including teaching group theory and then doing algorithms. And I just found almost all my computer science students like never, the two cases, one's never heard of it and one's heard of it, but think, what's group theory to do with anything? Because all they learn just like symbols, doing proofs, but there's nothing to do with, oh, you actually have a transformation, you actually have a cube can rotate around. I mean, not in this kind of concrete way. So I think that's really something missing. I would very much like to address that, like in like conferences like this or something. That's why I organized 3 competitions before. And this time we actually submitted a proposal for a workshop, and they just said, we're not interested. You don't have to have a workshop here this time. So, okay, whatever. But I really think this kind of a basic mathematical principled way is overshadowed right now by this machine learning, data-driven, bottom-up. And I would like to advocate anyone you can should address some fundamental principles with your students and in your own research. Yeah.
Thank you very much, Dr. Liu.
Thank you.
These 2 our last keynote speaker.
I leave this, right?
You leave. You can leave this. Yeah.
That's my timer.
Okay. The last speaker is Dr. He's already here. He's Dr. Mahit Gupta, and he's associate professor in computer science at the University of Wisconsin-Madison. He received his PhD from Robotics Institute, Carnegie Mellon University, and was a postdoc researcher in Columbia University. And he directs the Winston's lab with research interest in computer vision and computational imaging. He has received Best Paper Honor Mention awards at the Computer Vision and Photography conferences in 2014 and 2019, including a MAR Prize, and which is the Best Paper Prize, MAR Prize Honor Mention, which is the best conference best paper award on the ICCV. I would say the honor mention is the second best paper. And the Sony Faculty Innovation Award from an NSF Career Award, and which is pretty prestigious. And his research has been supported by NSF, ONR, DARPA, Sony, Snap, Cruise, and Intel. And his talk will be shedding light on 3D cameras. Dr. Gupta, you can go ahead to give the presentation.
Thank you very much. can you all hear me okay?
Sure. Well, you need to share the slide first.
Yep, I will share my slides. Let's see.
Currently, it's a little bit off.
Yep.
Yeah, right now it's good. Yeah.
Is this okay?
Yeah, pretty good.
Good, thank you. Okay, first of all, thank you for the invitation. And I also wanted to thank the previous speaker, Yangshi, for a really interesting talk. I think this is almost, it's a very timely talk because this is a good time to start thinking about computer vision from first principles and not just think about heuristics. So Yangshi, great talk. Thank you.
Thank you.
Okay, so I'm going to talk about 3D cameras. But before that, I want to tell a little story about light itself. Now, these days, it is common knowledge that light travels. It has a finite speed. I mean, it travels really fast, but still, it has a finite speed. This was not always the case. Till about 400 years ago, people used to think that light just travels instantaneously. It has infinite speed. Galileo was one of the first few people who thought otherwise. He believed that light actually has a finite speed, and he devised a simple experiment to show that. The idea was that he and an assistant, they got on top of two mountains, two hills. Each was carrying a lantern. And the idea was that first Galileo would turn on his lantern, the light would reach the assistant, at which point the assistant would turn on his lantern, light will travel back. And the hope was that Galileo would notice a finite time delay, right, which would establish that light has a finite speed. So this was a sound idea in theory, but hopefully you can all see what the challenge was here. Now, this was 400 years ago. Nobody had a high-speed stopwatch. They were relying purely on human perception to notice this time delay, right? And they were only about 1,000 meters apart, so light would have taken about a few microseconds to travel the distance back and forth, which was much faster than human perception limit, right? So in a way, this experiment did not work out. But the interesting thing is that despite this apparent failure, Galileo still made a reasonable conclusion, which is that either light travels instantaneously or it just travels too fast, right? So despite a failed experiment, he was still able to make out something from it. Example of good science. Now, fast forward 200 years ago, by the time people had started believing that, yes, maybe light does travel with a finite speed, but still there was no good way to actually measure the speed of light. Along came this French physicist by the name of Fizeau, who devised this really ingenious, clever experiment to measure the speed of light. So what we had was, again, there was a light source here, which was sending a beam of light, and there was a mirror placed about 5 miles away. And the idea was very similar in that they will turn on the light source, light will then travel to the mirror and then come back to the observer. And then they will somehow be able to measure this time delay. Now, in this case, they did place the mirror about much further than in Galileo's case. This was about 5 miles away. But unfortunately, again, this was still about 200 years ago, still no high-speed stopwatches. So it was still too fast, right? So light would have still taken, I'm sorry, I have a visitor. Just a moment. I'm sorry, it's a Sunday here and young kids at home. But anyway, so even in this case, even though the mirror was further away, light would have still taken about a few tens of microseconds, still too fast, right? Still wouldn't work. So Fizeau did not give up. He again came up with a really clever idea. What he did was he placed this rotating wheel in the light path. Now, what happens is that when the wheel rotates slowly, a light beam that travels through one of the gaps, it comes back through the same gap. So this observer this observer sees a pulsed light view, right? Light is alternatively blocked and visible, right? So this is fine when the wheel is rotating slow. But now, and here is where the cleverness comes in, he started rotating the wheel a bit faster. And what happens is that at the right speed of the wheel, any light beam that goes through one of the gaps gets blocked by the next tooth. So again, at the right rotation speed, the observer sees nothing. So with this observation, and by measuring the rotation speed of the wheel and the number of teeth, right, he was able to estimate the speed of light within 5% accuracy. Now, this is remarkable. This was done about 200 years ago without any high-speed timing instruments available. He was able to achieve this measurement. So I often tell my students that the next time you complain about not having resources, think about this experiment. This may be a way to ingenuity, to cleverness. So anyway, so again, fast forward 200 years, to current day, we now have very precise measuring instruments available to measure the speed of light, which we can now use to design cameras that can measure depths or distances. And we call these 3D cameras. And here is a very simple instance of a 3D camera. You have a light source, could be a laser. There's a sensor. In the simplest form, this laser emits a very short light pulse, which travels to your scene of interest and then gets reflected back. There's a high-speed stopwatch that measures the total time of travel back and forth. And now we do know the speed of light, which we can use using this very simple equation to measure the depth or the distance. Right? This principle is called time of flight, because you are measuring the time of flight or time of travel of light. And these cameras are often called time of flight cameras. Right? They're a very simple principle, but this now forms the workhorse of many commercial practical 3D cameras. There are many applications. One poster child application is autonomous driving. You must have heard of LiDAR. LiDARs are all based on this time of flight principle. Right, so this is one application, but then there's many other applications. Think about augmented reality, think about robotics, think about industrial automation. Essentially, any scenario where you want to measure the speed of, where you want to measure the 3D geometry or the 3D shape of the surroundings, right? These cameras are making an impact. Right? They're driving many new applications, self-driving cars, augmented reality. So there's a lot of excitement here. Now, as many of these applications mature, you're increasingly going to need higher and higher resolution, right? Yangshi talked about augmented reality applications. So think about AR settings. In order to get a real immersive experience, we do need to recover the 3D shape of surroundings with extreme details. But even imagine maybe a drone flying through a forest. It needs to resolve fine details like twigs and branches to navigate successfully, right? And just to be clear, at this point, I want to make a distinction between the spatial resolution and the depth resolution. Now, spatial resolution is just the number of pixels, right? And that continues to rise. But there are more fundamental limitations on the depth resolution of these cameras, which is the ability of a camera to differentiate to very similar depths, right? And that's important. So here is an example. Suppose we have a consumer-grade 3D camera looking at an object about 10 meters away, right? This is the kind of 3D shape that it can expect to recover right now, right? And this is a simulation result. Now, in this case, we had a reasonably high spatial resolution, about a megapixel, but the depth resolution is relatively low, right? It's only about a couple of centimeters. So with this, we can maybe tell that it's a human face, but not much more. Our goal is to get something like this, where there are sufficient details to perhaps not just say that it's a human face, but maybe even start recognizing the person. Now, this will require cameras with an order of magnitude higher depth resolution as compared to current cameras. For example, at 10-meter distance, you would like millimeter resolution instead of centimeters. Right, so an order of magnitude gain. And if this were not challenging enough, right, we are talking about an order of magnitude gain. So if this were not challenging enough, you would also like to do this with only consumer grade devices so that these are broadly accessible, for example, in consumer imaging. Now, all this sounds challenging, right? We're talking about an order of magnitude gain while maintaining a very strict budget in terms of cost, in terms of size, in terms of power, weight, etc., etc. Right? So this, again, all this sounds challenging, but fortunately, there is one imaging modality that is a good fit, that is at least a good starting point, and that is what we call continuous wave or indirect time of flight imaging. So here is a typical indirect time of flight camera. We also call this continuous wave time of flight. Again, we have a light source and a sensor. Now, the key difference is that the light source, instead of sending out these short pulses of light, the light source now emits light continuously, right? The intensity of light source is modulated over time at very high speeds. So, for example, the intensity could be modulated as a sinusoid, something like this. Now, the one thing to remember here is that this sinusoid, this is being modulated, oscillating really, really fast. So typically, it's of the order of tens of or hundreds of megahertz. So one oscillation gets finished in a few nanoseconds. Right? So now what happens is that this emitted light travels through the scene and then comes back to the sensor. Now, the brightness of this received light also varies as a sinusoid, but now this sinusoid is shifted in time, right? And the amount of this shift is proportional to the total travel distance, right? So if we can somehow measure this shift, we can compute the scene depths. Right. Any questions so far?
You can go
Okay.
ahead.
Yeah. Okay, great. Now the goal is to measure this shift. Now, one way to measure this shift is to directly sample this received sinusoid. Now, this will be a straightforward way of doing it, but this will require very high speed sampling. Remember, the period of the sinusoid is of the order of tens of nanoseconds. So you would need cameras with frame rates of millions or even billions of frames per second, right? This is not very efficient or practical. Instead, what these cameras do is compute the correlation of this sinusoid with what we call a demodulation function. This is also typically a sinusoid function. Now, it turns out that this can be done much more efficiently, right? So eventually what the camera does is measure a single intensity value, which is the correlation of this received light, this blue sinusoid, and this orange demodulation function, right? So essentially, this is this inner product or the dot product, or you can call it correlation. Essentially, this is an integral of the product of two functions. But ultimately, what you measure is just a single intensity value. Now, remember, the goal was to measure this blue sinusoid, which is the received light. Now, basic algebra tells us that a sinusoid has three unknowns. So we need at least three measurements, which are computed by, the three unknowns are the phase of a sinusoid, the offset of the sinusoid, and the amplitude of the sinusoid. So these three measurements are computed using three different correlations, using three different demodulation functions, right? Ultimately, again, I'm zooming out a bit now. Ultimately, what these cameras measure is these three intensity values. You can think of these as three measurements, which you can use to recover the three unknowns: the phase, the offset, and the amplitude. And remember, the phase is what gives us the depth, right? So this was a very quick primer on how these continuous wave time of flight cameras work, right? By the way, this method, this modality is the basis of many consumer-grade depth cameras, including the Microsoft Kinect. Many of you may have heard of the Xbox. The Xbox was using this device called the Kinect, which was based on this principle. Now, the newer version of these devices was called the Azure, again, which is based on this principle, right? Sony also has a line of devices which are based on this principle here, right? So, at a very abstract level, we can think of these cameras as a mapping from depth values to intensity values, right? This is a very important point. So I want to illustrate this. So imagine one of these cameras, right? One of these depth cameras, and let's say they are going to look at these points at a certain depth range. Now imagine a scene point at a distance d from the camera, right? Now we are talking about these three intensity values, I1, I2, and I3. And you can think of these three values as really the samples of the correlation function corresponding to this distance, right? Now, you can think of these three intensity values as a point in a three-dimensional intensity space. Now, this particular depth, this results in this intensity point. Now, let's say we have a different depth. We're going to get a different point in the intensity space, another distance, another different point. Essentially, if we look at all possible depth values in this range, they're going to map to a 1D set of intensity points that trace out a curve. And we're going to call this the coding curve. Right? Now, we can think of this coding curve as a geometric representation of a time-of-flight camera design, right? And this is a really important point, which tells us that the performance of any given time-of-flight camera now, we can determine by its correlation functions, which in turn can be represented as a coding curve. So really now we can explore the entire space of time-of-flight cameras in this geometrically intuitive space of coding curves, right? So essentially, this gives us a way to kind of abstract out the underlying hardware details, right? And really think of these cameras at an abstract geometric level. Now, from a functional standpoint, a coding curve defines a unique one-to-one mapping from depths to intensities, right? So, which means that every point on this curve corresponds to a depth and vice versa. Which means that now if the camera measures an intensity point, we can use some kind of decoding algorithm to compute the depths, right? Now, if we get a different intensity point, we get a different depth, and so on and so forth. Now, in the ideal case, if there is no noise, then we can do this decoding perfectly, right? Meaning, given an intensity point, we can perfectly measure what the depth or distance of the scene point is. But as Yang-Shi also alluded to briefly before, we are doing computer vision. Life is not ideal here. There is always going to be noise, meaning the actual measured intensity is going to lie somewhere in a noise ball around a true intensity, right? Because of this, there is always going to be some uncertainty in the estimated depth. And this uncertainty actually can be quite large. And this uncertainty results in low depth resolution. And just to emphasize, this is arguably the most important reason that limits the depth resolution of time-of-flight cameras, this depth uncertainty. Now, one way to reduce this uncertainty is to somehow increase the size of this intensity space, right? Something like this. If we could do this, if you could somehow increase the size of this space, then the same amount of noise will result in smaller depth uncertainty, right? Because now a smaller fraction of this curve intersects this noise ball. It maps to smaller depth uncertainty, a lower depth range, right? So that results in higher depth resolution. So this sounds fine in theory, but unfortunately, increasing the size of the space requires increasing the scene brightness values, which we don't have any control over, right? We cannot really increase the brightness of the scene points, right? We cannot increase the scene albedo or reflectance. Another way to do this is to increase the light source power itself, again, which is usually fixed due to limited power budgets. It's a very practical constraint, right? So again, in theory, we could increase the depth resolution by increasing the size of the space, but in practice, this is just not possible, right? So our key idea was that if we think about why we wanted to increase the size of the intensity space, it was actually to increase the length of this curve. Well, ultimately, it's the length of the curve that we are interested in, right? The main idea is that it is possible to have longer coding curves, but within the same space. For example, something like this. Now, this is a longer curve, and this curve may have different geometry, and it may require a different set of correlation functions. But as long as these curves, these functions are physically realizable, we will get the benefits of longer curves, meaning lower uncertainty and higher resolution. In fact, we were able to derive a theoretical expression that relates the coding curve length to the depth resolution. And this expression told us that everything else being the same, the resolution is actually directly proportional to the coding curve length up to a first order approximation. Okay? So this was a nice, intuitive result. And again, intuitively, it does make sense, if you think about it a little bit after the fact, but it was nice to be able to get this mathematical validation that really the depth resolution of a camera is directly proportional to the coding curve length. Now, the reason why this is interesting is that the coding curve length is a fairly intuitive geometric property, and it is almost trivial to compute for any indirect time-of-flight camera, which means that now this single common expression can be used to analyze the performance of many different time-of-flight cameras, right? And again, this is important because oftentimes you go and buy a camera, and it is very hard to predict its performance because it depends on so many factors, like the underlying hardware and stuff like that. But now, this approach gives us a way to kind of abstract out all the hardware details and really think about these cameras from a very theoretical, from a very principled perspective. So let's look at a couple of examples. One of the most popular time-of-flight camera design uses these sinusoid functions for both modulation and demodulation, as we just talked about. In this case, the correlation functions are also sinusoids. And it turns out that here the coding curves, they are circles. The radius of the circle is given by this expression here. And here K is the number of measurements. Remember, we talked about requiring at least 3 measurements. So 3 is the minimum number of measurements. And for many typical time-of-flight cameras, they often take 4 just to get more robustness. Right? So the coding curve length here is just the circumference of the circle, which is 2 pi r. This is the length here. Right? Now, another popular coding scheme is where instead of sinusoids, we use square modulation and demodulation functions, so square waves, something like this. In this case, their correlation functions, which is the correlation of modulation, demodulation, are these piecewise linear triangular kinds of functions, something like this. So any guesses what the coding curve would look like in this case? I cannot see the audience, so feel free to just shout out. Any guesses? Like for sinusoid, we had a circle. What would it be here? Take any wild guess. Circle? Here, the one clue is that these correlation functions are piecewise linear. So perhaps the curve will also be kind of piecewise linear. It turns out that it's actually a polygon. It's a non-planar hexagon, actually. In general, it's a polygon with 2 k sides. Again, remember, k is the number of measurements. And it turns out that the length of each side is 1 over square root k. So the total curve length, it turns out, is 2 times square root k. So now what we can do is compare these 2 different schemes purely in terms of their coding curve lengths, right? We can place them side by side. We can look at the ratio of these 2 things, ratio of these 2 curve lengths. This tells us that everything else being the same, square coding achieves approximately twice as much resolution as sinusoid coding. And we can actually verify this theory using experiments that I'll show later. right? So again, now suppose you have two different cameras and you're asked to compare their performance. You can do this without doing any experiments, purely theoretically, by analyzing their modulation functions. Right. Now, this is only theoretical because square coding requires higher bandwidth and stuff, but this is just an example to demonstrate how different time-of-flight camera designs again can be analyzed using this purely geometric representation. Now, the next, perhaps more important question here is, can we use these geometric ideas to design new high-performance cameras and not just analyze them? Can we use these intuitions and this theory to design better high-performing cameras? Now, one way to think about this design problem is as an optimization problem. You can do this optimization in the space of these modulation and demodulation functions. So the question here really is, what are good modulation and demodulation functions which give you high performance? Now, thinking directly in the space of these functions is a little bit challenging because this is a high dimensional space. So instead, what we do is we say, what if we do this optimization directly in the geometric space of coding curves, right? Which is a little bit more intuitive. For example, we just said that longer coding curves are better, right? That longer the curves, the better the resolution. So let's use this intuition to design some curves. Here is one example. This is a curve. This is long, but the problem is that it intersects itself, right? Meaning the mapping from depths to intensities is not unique, right? And we wanted this mapping to be unique, right? So this is not good. Here are two more candidates. This is a helix, and this is a Hilbert space-filling curve. Now, both are long curves. Both are non-self-intersecting, which is good. But the one problem with these curves is that they are not distance-preserving, meaning there are points on the curve that are close in the Euclidean sense, right? But they're far along the curve, right? So even a small amount of noise can result in large errors because points can kind of jump around between different arms of the curve. So that's not good. So ideally what we want are curves that are long, that are non-self-intersecting, but they also have some nice locality-preserving properties. And one family of curves that satisfies all these properties is what we call Hamiltonian cycles on hypercubes. Now, we were talking about this intensity cube, right? We can think of this intensity cube as a graph, right? A graph in this discrete math sense, where the vertices are the corners of the cube and the edges of the graph are the sides of the cube. Now, with this, now we can make a Hamiltonian cycle which visits every corner of the cube exactly once. And for now, we're going to remove the origin and this diagonal vertex for practical reasons. But this curve visits every other vertex. If we think about this cycle here, this curve is actually quite long. In fact, its length increases exponentially as a function of k, which is the number of measurements, which is also the dimensionality of this cube. And furthermore, this is also some nice provable distance preserving properties, meaning if 2 points are close along the curve, then their Euclidean distance is also small and vice versa. Right? So in a way, this curve has all the nice properties that we are looking for. So what we're going to do is, based on these ideas, we're going to propose a new time-of-flight camera design that uses this Hamiltonian cycle as the coding curve. Right? So this is now our coding curve. And again, you can imagine that this is kind of a piecewise linear kind of a curve. Now, if we go back to the correlation functions that produce this curve, they're probably also going to be piecewise linear. And they actually look something like this. They have this trapezoidal kind of shape. Right? And we can use these functions now to implement new time-of-flight cameras with this kind of design. Now, this is for 3 measurements. So our cube is in 3 dimensions. But if we have 4 measurements, we can again make a cube in 4 dimensions, right? And again, we can make a cycle in 4 dimensions and create similar functions, and so on and so forth. If we have 5 dimensions, we can make a cube in 5 dimensions and make the cycle, and so on, right? So in 4 and 5 dimensions, our functions look like this, right? So again, they all have this kind of trapezoidal structure with increasing frequencies, something like this. And we can generalize these ideas to any number of measurements. I'm just showing 3, 4, and 5. Right. Now, earlier we were talking about coding curve lengths, right? And the coding curve length being a measure of how good these cameras can be. So here the x-axis is the number of measurements, and the y-axis is the coding curve length. So if you remember, for sinusoids and square, the coding curve length increases as a function of square root k. So as you take more and more measurements, the coding curve length and the depth resolution increases, but it's a slow growth, square root k. But for Hamiltonian functions, it increases exponentially, which means that, or this suggests at least, that we should be able to achieve much higher depth resolution with these Hamiltonian codes, right? So next, I want to show some results. So far, we have been talking about theory, but let's see if this really works. So first, I'm going to show some simulations. So we wrote a renderer for time-of-flight cameras, right, to simulate, to evaluate the performance of these things in simulations. So here's an example. There's a camera looking at a face about 10 meters away. And here are the recovered shapes using different coding schemes with the same number of measurements, right? So a couple of things to notice here. First, square coding does better than sinusoid coding, as our theory predicted. But with Hamiltonian coding, we are now able to recover sufficient details again, so that we can perhaps start recognizing the person. And just to make this comparison fair, you know, we had everything the same number of measurements, the same power in the light source, the same distance, and same everything. Right? Here is another example, you know, kind of motivating long-range 3D imaging. Let's say you want to build a 3D model of an outdoor structure for maybe virtual reality or maybe for virtual tourism, etc. Here are the recovered shapes using different schemes, so sinusoid and Hamiltonian. And you can look at the average error. You see about an order of magnitude improvement, again, which is approximately what is predicted by theory, about an order of magnitude gains. So, I mean, at this scale, even the sinusoid coding does recover the overall shape. But if you really zoom in, you can see the difference. With Hamiltonian coding, you can start making out intricate details like these individual bricks, which can be very important again for virtual reality, augmented reality applications. To really get immersive experience, you really need to make out all these details. But even for, you know, like robotics applications like navigation, etc., which is the focus of this workshop, imagine there's a robot which is trying to climb this staircase. And let's say it's using a depth camera to get the structure of the staircase, right? So this is the ground truth shape along a vertical scan line. And just for effect, we added very strong noise, which could happen if there is, you know, if there is a lot of sunlight, ambient light, or if the light source, the laser doesn't have too much power because of limited battery. So all these factors can result in a lot of noise. And because of noise, with the conventional coding schemes, you can recover shape like this, extremely noisy, right? Both sinusoid and square. Right, so there's a lot of noise here due to strong ambient light, and as you can see, the underlying geometry is almost completely lost. This can make navigation extremely difficult, extremely challenging. Now, with the same total power and same total capture time, Hamiltonian coding recovers something like this. Right, it's still noisy, but you know, at least the underlying structure is better recovered. And at least in this case, an improvement like this could make a qualitative difference, perhaps enabling a robot to successfully climb the staircase. Right. Now, this was simulations. Now, the next very important question was, how do we go from theory and simulations to a real practical hardware implementation, right? Can we ever implement this in real devices? The one key challenge here for us was most current consumer-grade time-of-flight cameras like Microsoft Kinect, they were mostly limited to sinusoid or square coding, right? And we did not have enough low-level access to implement these new kinds of coding schemes. So to demonstrate our approach, we built our own time-of-flight camera, just a proof of concept prototype, which can implement arbitrary modulation and demodulation functions. Now, there's all kinds of stuff here. There is a laser diode that emits light, which goes to the scene. Here's a scene, and then comes back to a sensor, which is currently a single pixel, but of course you can capture an entire scene by scanning. There's many other components here, but hopefully, eventually, we could miniaturize this on chip. In fact, right now we are working with a company which has provided us with a configurable time-of-flight camera, which is pretty miniaturized, but we can now maybe start implementing our customized arbitrary codes there. But with this, I want to show some real experimental results now. So here is a scene. It's like a staircase that I showed earlier, 3 planar patches. And this is the depth recovery results. Again, the staircase structure, it's almost completely lost with this conventional sinusoid coding, but recovered reasonably well with Hamiltonian methods. Now, one thing you will note here is that the improvement in real experiments is lower than the simulations. It's not one order of magnitude. It's maybe 4 or 5 times. But this is because the current hardware prototype, it is not optimized to implement Hamiltonian coding. But hopefully this can be addressed with the optimized hardware in future. So one thing I wanted to emphasize that these new camera designs that I just talked about, these are by no means theoretically optimal, right? But the hope here is that by using these geometric tools, these geometric ideas, we are hoping that, you know, it really just enables people to maybe think about these design principles in a geometric way. And hopefully it enables people to design curves which can do better, right? Now, these new curves could be small perturbations of these Hamiltonian curves, or maybe something completely different. In fact, if any of you has any ideas, I would love to talk with you more. At this point, I think I am nearly at the end of my time. I did have a few other things, but maybe this is a good time to stop and take questions. So, yeah, thank you very much.
Thank you, Dr. Gupta. Any questions? I have a question. Actually, I'm seeing the coding curve. If my understanding is correct, it's actually you are increasing dimensionality of the curve actually the lighting part, and all we can say that is the increasing the dimensionality of the calculation of I would say the depth estimation, and in order to get the higher depth resolution. But if that is correct, if increasing the dimensionality and nothing is something like I would say nothing is free lunch, right? And you will I would say I would imagine that would sacrifice some of the I would say time performance. And actually, time of flight sensors, one thing that is accuracy, that is very important. And another thing is the time performance is also, people consider time of flight cameras are actually very fast and very quick.
Yes.
And would you current algorithm be much slower or similar like the normal time of flight cameras, and with currently your coding curves applied?
That is an excellent question, and thanks for asking that. So you can think about increasing the performance of these cameras almost along two different axes. One is just by increasing the dimensionality of the curve, right? So for example, if you purely limit yourself to sinusoid coding, instead of taking 3 measurements, as I said, let me go back actually. Yeah, I think this is a good thing here. So on the x-axis, you can increase the number of measurements, which is increasing the dimensionality of the curve. So if you purely limit yourself to, let's say, sinusoid coding, the performance can improve just by increasing the dimensionality, right? But what we are saying is that even if you limit the dimensionality, let's say even if you limit yourself to only 3 measurements, so 3-dimensional, you can still improve the performance by using different kinds of functions. So go along the y-axis, right? So for example, if you limit yourself to only 5 measurements, so 5 dimensions, you can see that the performance of the Hamiltonian curves is higher than the corresponding 5-dimensional sinusoid function. If you limit yourself to only 3 measurements, then the performance of the Hamiltonian curve, the 3-dimensional Hamiltonian curve, is more than the corresponding 3-dimensional sinusoid curve. I hope that makes sense. So essentially, you can stay within 3 dimensions and still improve performance by using these Hamiltonian functions. But of course, you can get more gains by increasing the dimensionality as well.
Okay, thank you. Do you have a trader? What is the best number for the dimensionality of the curves?
That's a good question.
I would not think that is the higher the better. There must be a trade-off. At some point, you apply the curve numbers that will not increase significantly.
Exactly. No, that's a great question again. In theory, higher the better. But in practice, as you said earlier, ultimately you will start running into a trade-off where, as you capture more and more measurements, you're going to lower the effective frame rate of the camera, right? So ultimately, the optimal number or the sweet spot will be determined by your application constraints, like what's the minimal frame rate that you need. So that will provide the real constraint. So there'll be a sweet spot somewhere in the middle. So as an example, many commercial time-of-flight cameras these days, they take maybe anything between 6 to 9 different measurements. So K for those cameras is about 6 to 9. So 6 to 9 dimension curves. And even with those 6 to 9 dimensions, we can get significant gains by using these Hamiltonian functions.
Okay. Thank you very much, Dr. Gupta. Yeah.
Thank you.
We run out of time, and we will leave with the next one. Thank you very much, Dr. Gupta. We will live stream that. Probably more people will contact you after live streaming, watching your video offline.
Absolutely. Thank you very much.
Thank you. So the next one is Dr. Liu. Yeah, and she will give us the talk on the topic of network specialization, where feature level knowledge distillation, and the group is from Cisco, and which is Dr. Liu and Yuzhang Shang, and from Illinois Institute for Technology, Yugo Yao from Michigan University, and Ramana Compella from Cisco Research as well. on with computer audio or not? 照了，一会儿 mute 就可以了。mute 一下就可以了。然后 share the screen 就可以。
Thank you for your patience. There were some security issues with my laptop. Hello, everyone. My name is Gawen Liu from Cisco Research. And today I'm going to introduce our work, network specialization via feature level knowledge distillation. First, let's talk about why we propose this work. The motivation to propose model specialization is because specialized neural network has recently become common for edge devices. Usually, neural networks are trained for general purpose, and these models are not optimized for specific tasks. And the parameters for these models are usually redundant. So, but different applications and different users may have unique requirements or constraints that cannot be met by a general purpose model. So we propose the knowledge distillation, which can efficiently regularize the knowledge transfer process to a small task-specific model. So this approach is particularly useful for resource-constrained devices, such as mobile phones or IoT devices. The purpose is to minimize the model size and reduce the inference time. So one question you may ask is, why not fine-tune a model? Because the best way and to implement a specialized neural network is to fine-tune the model. The problem with fine-tuning is the fine-tuned model will maintain the model size, and it's not a good solution for edge devices. If we want to deploy a neural network on edge devices, we need a smaller neural network. And so we think knowledge distillation is a solution for this model specialization problem. Knowledge distillation usually has a large teacher network and a small student network. The key idea is to transfer knowledge from the large model to small model. And the teacher model is learning knowledge from the data set, and the student model is learning knowledge from the teacher. Knowledge distillation is first proposed by Hinton. And this problem setting is widely required by industry for real-world deployment of deep learning algorithm. For example, if a customer wants to detect vehicles, he may not need to detect animals. This is our proposed framework. The orange blocks represent the teacher model, and the blue blocks represent the student model. We propose a feature-based knowledge distillation, which means we are learning the similarities between the feature maps of the student model and the teacher model. The key idea of the knowledge distillation is to force the student model to mimic the performance of the teacher model. So the ultimate goal of knowledge distillation is to minimize the distance between teacher and student for optimizing the student's parameters. From the previous framework, we can see the architecture of the teacher model and student model are different, especially the last layers of the teacher and the student model. So the conventional logic-based knowledge distillation won't work. So we propose the feature level knowledge distillation. And the knowledge distillation loss compose two parts. The first part is feature-based knowledge distillation loss. And the second part is the feature-based leap-years knowledge distillation loss. So the overall loss is a combination of knowledge distillation loss and the cross-entropy loss. Here are the experimental results. We evaluate the model performance on CIFA 100. The teacher model is using wide ResNet with 28 layers and a widening factor of 4. And the student network is using wide ResNet with 16 layers and a widening factor of 4. We compare our results with both training from scratch and fine-tuning on 5 sub-data sets with 20 classes, 40 classes, 60 classes, and 80 classes. From the performance, we can see the knowledge distillation outperformed the other traditional algorithm, traditional methods. We also plot the feature representation of and compare the feature representation between training with knowledge distillation and training from scratch. From the results, we can see the training from the feature representation, training with knowledge distillation are well separated. So it means it learn a better feature representation. So in this work, we propose a novel knowledge distillation framework that address the challenge of constructing specialized network for simpler tasks with small data sets. And the proposed framework overcome the problem of overfitting in specialized neural networks by allowing the student model to learn a better representation from the more complex teacher model. Our experimental results have demonstrated that the proposed framework is effective in improving the performance of specialized network training, especially for simpler tasks with small data sets. If you have any questions, I'm happy to answer. So far, we haven't tried to deploy or test on hardware. That's the next step. I think the first step, we design the algorithm and we are working on open source project and we will release the code of these model compression toolboxes maybe in half a year. And the next step, we may test on some Cisco Meraki cameras. That's the plan.
Cisco own camera.
Cisco has a Meraki camera.
I don't know that actually. Okay, any other questions from the audience? Okay, if no, thank you very much, Dr. Liu. Next one, I don't think it's online right now. is Hartheim, Hosen, Ibram here? No. Okay. Probably we can move forward. With the next one. The next presentation is panoptic with integrated panoptic segmentation for visibility estimation at light and night, and presented by Hidemato Sakino from Weather News Incorporation. Yeah, everything works fine. Oh, we need to mute. Share the screen. Okay, good.
Good evening. My name is Hidetomo Sakino. I'm from Weather News, Japan. Today, I'd like to present my recent work, Panoptic Biz. Motivation for auto driving and drivers, high visibility on the road is required. Visibility distance or level estimation is important to know, even at twilight and night. However, weather and illumination conditions are critical issues, such as rain, snow, fog, low brightness, reflection, strong LED, and raindrops exist. How to estimate visibility distance and level for such single camera images under adverse conditions? I first tested several SOTA method, like all-in-one gear models on CVPR 2022. However, all images like raindrops and twilight scene have become degraded. Even in these heavy snowfall scenes and low light scenes and the local strong illuminated scenes, just segmented results became like this. The even 2023 paper, no snowfall removal or fog removal has been obtained. Here is a deep depth improvement. Even in this, you can see a spotlight or headlight here. And if we simply apply the CVPR 2022, no clear depth information obtained. So we first use applied computer vision to smooth or eliminate this strong local spot and obtain the depth. In summary, related work like FIFO CVPR 2022, I expected this paper, for example, learning fog invariant features for foggy scene segmentation. However, no good result obtained. And even see databases like famous cityscapes with 3,000 images. These databases do not contain heavy rainfall, snowfall, and even no or less twilight and nighttime scene. This shows proposed practice this. We give physical distance in advance by design by this annotated like this 500 meter, 1000 meter, and pre-trained by daytime and nighttime. At the same time, trained by improved depth map and deep scene combined way. And this is an inference step. Input unknown one single images. Deep reject has been applied in order to reject impossible or difficult images. For the other images, deep scene and deep width has been applied. These are all transformer based. Now I summarize here. This panoptic disk consists of 5 deep learning models, deep scene to deep reject. And we have created a new training data model like cityscapes. This is an example of the experimental results. You can see adversarial scenes like heavy snow scenes, night scene, and foggy scenes. Incomplete semantic segmentation images have been obtained. However, our proposed method segmented well. In another example, this is a daytime scene and 2 nighttime scene. You can see heavy snowfall. SOTA have been negatively impacted by external conditions like weather conditions. However, our proposed semantic segmentation results shows much more stable results. These are simulated results at nighttime. And compared with CVPR 2022, you can see no sky and road has been obtained under the heavy foggy scene. And this is a real foggy scene. And see here is a visibility levels, L1 to L3. Here is the ground truth and estimated classified physical visibility level. And here's a quantitative results. And panoptic width shows best when we combine 5 deep learning models. This is from YouTube, onboard camera, and this is a camera onboard is on the police. And you can see no stormy scenes. And this is a real-time visibility estimation. And sometimes rejected as low visibility. And at the same time, weather condition like heavy snow or light has been obtained. Now, here's a conclusion. It is the first time to estimate physical visibility distances under such adversarial visual conditions. Thank you very much.
I want to ask whether this data set is owned by your company right now, or is already published?
Not published.
Not published.
We own collected in Japan region mainly.
Okay, and is there any plan for in the future publish that data for the community?
Maybe we will not.
Yeah, because I can see there are quite a lot of challenge things and which we don't solve that right now, and I would say that is very useful and for in the future. I guess that is what your company is actually focusing on.
Most of data has been purchased by customers, camera-based data. So we need to get permission or NDA, something like that.
Yeah,
Okay.
I understand. Okay. Cool. Any other questions? Okay, thank you very much.
Thank you very much.
Actually, I can see the last presentation is here. Hard time, are you here? For the paper, ST room net learning room layout estimation from single image through unsupervised spatial transformation. Are you here? No. Okay. Let's go to the next one. So, Sriram, you are here, right? Okay, you are here. Okay. Can you go ahead to try your presentation mode? I cannot hear you. Probably. Can you hear me? Sriram, can you hear me? We try text. You can see. Okay, now I can hear you.
All right, great. Yes.
Okay. Finally, it works. Okay. Let me introduce the Sriram and Krishna is from Samsung Research, and his presentation is deep, smooth, efficient, and smooth depth completion. You can go ahead.
Yeah. All right. Yeah, good evening, everyone. I'm Sriram, and I'll be presenting our paper Deep Smooth today. Right. Before I get started, firstly, a very quick background on depth estimation, as I'm sure all of you already know. Depth estimation is a fundamental task in computer vision, and it involves estimating the distance or depth of every pixel in an image. It is useful across domains from augmented reality to robotics, and it is a prerequisite step in spatial mapping, video portrait effects, etc. There are many paradigms which exist for acquiring the depth, and I'll very briefly talk about them. So firstly, we have monocular depth estimation, wherein we estimate the depth from a single RGB image. Then we have multi-view stereo and binocular stereo, where we utilize, say, a sequence of RGB images and their known 6DoF codes. Then we have commodity depth sensors, such as the Kinect and other ToF and LiDAR sensors, which extract the depth directly from a depth sensor. And finally, we have the paradigm that our work is using, which is depth completion, wherein we use an RGB and a sparse depth image to further refine and densify the depth image. So in the face of all of these paradigms, why do we go for depth completion? And the answer to that is that every paradigm has their own drawbacks. For example, in monocular depth estimation, it is geometrically not possible to extract the accurate metric depth from a single image, even though current neural networks do quite well thanks to large data sets. Then we have stereo imaging, which can tend to fail in textureless areas such as plain walls. And finally, we have depth sensors, wherein we have a multitude of depth sensors which have their own drawbacks. For example, the depth may be sparse and contain a lot of holes. There may be error in highly reflective areas, and so on and so forth. With depth completion, we aim to overcome these issues by combining the best of both worlds. We refine the sparse and noisy depth image with the semantic cues from an RGB image. Now, there has been a lot of contemporary work in depth completion, which I will briefly summarize over here. So most contemporary work right now, they use neural networks and they feed in an RGB image and sparse depth as input to produce a dense depth map. So these are typically designed to work on individual images rather than video streams. And when we apply this to a whole video, we notice that there is flickering depth over time, especially if the holes in the input are large and varying. So the noisiness in the depth map output propagates errors in downstream tasks, such as 3D scene reconstruction. So this is the primary motivation for our work, to make the depth completion smooth. So coming to our own contributions. Firstly, we propose a novel architecture that is carefully designed to model RGBD streams of indoor scenes with semi-dense input depth. Our network uses address-gated convolutions to encode the input depth, and R2+1D convolutions for spatio-temporal fusion, both of which I will get into detail later. Furthermore, we develop a novel loss function, which we call temporal planar consistency, that propagates the planes in the predicted depth over time and minimizes the distance between these planes in consecutive predictions. In this way, we enforce spatial and temporal consistency in the depth predictions simultaneously. And lastly, we validate our approach with some extensive experiments showing competitive results in depth completion while improving upon the other models in terms of temporal consistency. This is a brief overview of our model architecture. So I show this first just to illustrate the architecture, and I will get back to this in more detail. So as input, we have our color image and the semi-dense input depth, which, as you can see, contains a lot of holes. Just turn on the laser pointer. Yeah. And we have a dual branch encoder, both for the RGB image, the color encoder, and for the depth image, both of which are fused into a temporal encoder, which takes in information from previous timestamps and fuses it into a feature volume. And finally, we have a decoder, which outputs the dense depth image. Now, going to more detail about the architecture of each of these components. Firstly, we have the color encoder, for which we use a recent monocular depth estimation model known as MIDAS. This is used as the color backbone to extract features more useful for depth completion as compared to, say, any standard network trained on imaging. Then we have our depth encoder. So here we face an issue that in that our depth contains holes. And when we use naive convolutions to encode this depth, performance is affected. So we make a few changes in the form of address-gated convolutions. So to take this step by step, firstly, we have gated convolutions, which are a variation of a traditional convolution, where the output is gated using a second convolution. So you can think of this as a sort of a primitive attention map, basically where a second convolution is used to control and basically mask the output of the primary convolution. So this formulation has shown improvement in many image inpainting tasks, which is the primary reason for us using it over here. However, a key drawback with gated convolutions is that it effectively doubles the size of the depth encoder. And thus, to bring it back to a moderately sized model, we use address or dilated convolutions to reduce the size of the model. So then we have a temporal encoder, which consists of a sequence of R2 plus 1D convolutions. So R2 plus 1D convolutions are a factorized form of 3D convolutions. Basically, a 3D convolution is broken down into a 2D plus 1D convolution, which operate over the spatial and the temporal domains independently. In this way, we can save on the compute, as a 3D convolution requires a lot of compute and memory. Breaking it down in this way, we can use it with much less compute, as well as make it available for running it on device, as 3D convolutions are typically not supported in on-device frameworks. And finally, we have our decoder, which takes in the RGBD temporal vector as the input. And our decoder is a lightweight variant of the RefineNet architecture. And it contains skip connections from both the color and depth encoders for effective information propagation. So very quickly, just to reiterate, we have our color encoder based on the MIDAS monocular depth estimation model. Then we have our depth encoder, which uses address-gated convolutions to more effectively encode the depth which contains holes. Then we have our temporal encoder, which contains a sequence of R2 plus 1D convolutions. Our second primary contribution is our loss function. And before going into the details of the loss function, first I would like to talk about the desired characteristics of an ideal depth computation model. So firstly, we believe that the predicted depth must be consistent over time, which is to say that the predicted depth must be temporally smooth. And finally, and this is true especially in the case of indoor scenes, which are planar in nature, the predicted depth must be well fitted by planes in the scene. Your floor, walls, and ceiling all should be well fitted by planes in your depth prediction. And this we note as spatially smooth. To drive both of these characteristics forward, we have our loss function, temporal planar consistency. And a high-level overview of how it works is as follows. So we have our depth prediction at time I-1, which is to say d(I-1). We warp and reproject it to the current time step, ti, using the available 6 degrees of freedom force. We fit planes to this reprojected depth using the ransack algorithm for each plane, which it will then give us the plane equation, the coefficients of the plane equation. Then our next step is to flatten the values of the pixels such that they fit the plane exactly. We can get the value of this flattened pixel by inverting the plane equation. So as I'm sure all of you know, the plane equation is just ax plus by plus cz plus d equal to 0. And we can invert this equation and calculate the ideal value of z, that is to say the depth value at which it fits the plane exactly by inverting this equation. And as I mentioned before, we get the coefficients of the plane equation calculated by ransack algorithm. Our final temporal planar consistency loss is given simply by the L1 norm of this warp and flattened depth and the depth prediction at the current time step. To reiterate, we have the depth prediction at the previous time step, which is warped forward and then flattened to ideal planes. And then we compute the L1 distance with the prediction at the current time step. The key idea is that we enforce that the planes present in the previous time step continue to be present in the current time step. And in this way, we enforce spatial and temporal consistency simultaneously. Now, here we have a key note. The loss as formulated encourages the prediction of an idealized depth. Minor irregularities in the real world are flattened into smooth planes by design. So this encourages our model to avoid predicting fine details in favor of smooth planes. And this inevitably leads to a slight increase in error. And our main argument is that in most applications beyond a point, the temporal consistency in the depth output is more desirable than millimeter level accuracy. In the pursuit of accuracy, we must not have noisy and flickering depth, right? That would lead to a poor user experience and basically lead to propagate errors in downstream applications. Now we have firstly some quantitative results on the ScanNet dataset. And here I have some results with state-of-the-art methods from recent years. And 3 metrics. Firstly, we have RMSE and MAE, the root mean square error and the mean absolute error. And then we have our temporal consistency. So our temporal consistency is a metric which evaluates the smoothness of the prediction over time. It basically quantifies the percentage of pixels which are stable over consecutive predictions. That is to say, the ratio of change between them should not go beyond a threshold, which is arbitrarily chosen. Now, if you could pay attention to this table, you will notice that while our model has achieved the highest temporal consistency, it slightly falls behind in RMSE and MAE. This falls back to what I just mentioned. In the pursuit of smoothness, our model will predict slightly less detail. And because it is predicting slightly less detail, the error will slightly go up. But if you could also notice that the margin of error is the order of a few centimeters at most. And we believe that this is an acceptable trade-off for applications in which smoothness is more important than absolute accuracy. Right. Now we have some qualitative results on the ScanNet dataset. Right. What I would like to point out, if you could pay attention to this image where we can see the folds of the bedsheet in both the input depth and in the ground truth depth, it is visible that there are irregularities in the depth because the bedsheet itself is not a completely regular surface. It has bumps and so on, which causes the same bumps to reflect in the depth image. And we can see a similar output in all of the other methods as well. However, our method deep smooths, these bumps are not really visible and it is smoothed over into a planar surface. And in this way, it is both smoother and it has a loss of detail, which leads to a slightly higher error. Lastly, we have here a sample video. It looks like I'm not able to. Yeah, what I would mainly like to point out from this video is that other methods, we can see a sort of a flickering in the depth over time. And this is comparatively lesser in our deep smooth model. So in conclusion, we propose deep smooth, which is our depth completion method, which generates dense depth maps from semi-dense input depth using a novel dual branch encoder-decoder network. Our model is designed for video streams of indoor scenes by integrating R2+1D convolutions into the network for stable predictions over time. And we enforce spatial and temporal consistency by means of a novel loss function, which is our temporal planar consistency loss. Crucially, we argue that temporal consistency is a more desirable characteristic in applications where millimeter level accuracy is not required. Depth sensors are limited in their own accuracy due to engineering constraints, cost, and so on. providing high-quality depth maps through depth completion unlocks the way towards for applications to understand the 3D world around us. Yeah, thank you. If there are any questions, I would be happy to answer.
Thank you. One question is, what if you don't use the temporal loss, and what would be the result? Have you tested that?
Could you repeat that question?
You have the temporal loss as one of your main contributions, right? And
Yes.
what you don't have, if you remove the temporal loss, and what would be the result here?
Yeah, the result is as expected. In our paper, we have added an ablation for the same. So the temporal consistency goes down, whereas the RMSE and the MAE both go up.
Okay, and what about the color images? And if you remove the color images, would be that would finally the completion result would be much worse or slightly worse?
Removing the color image?
Color images, yeah.
Okay.
Only input the depth images.
Okay, so we have not looked into that setup, but in general, using depth images only reduces the performance because we do not have the semantic cues from the color image to rely upon to fill in the depth.
Okay, okay, yeah, that makes sense. And if there is no further questions, we will have the last talk. Thank you very much.
Yeah, thank you.
The last one is ST RoomNet, learning room layout estimation from a single image through unsupervised spatial transformers, and the authors are Haitham Hossein Ibrahim, and I think you are here.
Yeah.
Okay. Can you try to
yes, can you hear me?
Can you try to?
Hello, can you hear me?
We couldn't see your screen right now.
Yeah, okay.
I can see you. Yeah, you can share a screen. You can try to share a screen. Yeah, they are from National University.
Okay.
I can still see your face, but not the slides.
Right.
Maybe you change the screen to share.
Yeah. Yeah. Now the screen is shared.
Okay, it works now.
Oh, okay. So I'm Haitham Ibrahim. I'm a postdoc in the Multimedia Information Processing Lab in the School of Information and Communication from Chonbuk National University in South Korea. So I'm going to present ST RoomNet learning group.
Hello?
Unsupervised spatial transformation. Cover world proceeding boundaries from a single group image. The room layout can provide a better understanding of 3D scenes. The layout of the room is usually estimated by detecting key points like here, prediction of the key point or the planar segmentation. Like the key points here, we can find like key points of the different corners, and for the segmentation, we segment like the different walls or the different planes of the group. As a background, like there are two popular datasets for room layout estimation. The first dataset is the L-Fund room layout estimation, which is consists of 4,000 training images and 394 validation image and 1,000 testing images. Also, there's a dataset consisting of 209 training images, 53 validation, and 105 test images. Also, I like to revisit the Spatial Transformation Network, STN. STN is a learnable module which explicitly allows a spatial manipulation of the data within a network. Also, this module is differentiable module, and the use of spatial transformation results in model which is invariant to translation, scale, rotation, and more general warping. Here we show like affine transformation, which was a basic transformation presented in this paper, CN. And here this equation shows like the different parameters, like the network is trying to learn like the sampling kernel, also the interpolation kernel for here. In the proposed method, actually, we use extract the features of an RGB image, and then we use fully connected we predict 8 different parameters, actually not 9, because usually this parameter is 1. So we predict 8 different parameters, which is used for the spatial transformation layer to transform a reference layout. This is actually a fixed layout with a required layout. We use here a perspective transformation layer instead of a fine transformation, which is proposed in the original STN paper. Here also we propose a general hypothesis. Here, usually in Elsan, for example, or Hido, they have different labeling for each room type or floor or ceiling. So here we make all having the same. We make all the layout labels on all cases, which have a reference case here. For example, in some usually if the room size are 2, they just label left and right. Here, we know from the reference layout, it should be the frontal wall in between the right and left wall. And that's somehow a correction happens to the labels of each one. And also for the case of Hido, they have different different labels of our labels, so we just correct the labels to our standard labels. So here, we propose a modified spatial transformation network. In this case, we predict 8 different parameters. These 8 different parameters are used for the spatial transformation layer to transform the reference layout to the required layout of the room. We use 2 different feature extractors. First, the convex timing, the notation of convex timing. Also, we use the modified version of exception. Actually, in both of them, the bitwise convolution are used. Also, here, the blocks, this box is 3 times, 9 times, and 1 is 3 times. Also, this is a similar architecture to the exception. Instead, we cut all the blocks after the repetition of the middle block, and there is no exit flow. It is removed, and also this architecture is already presented in other previous features. The loss function used to learn this text is Hooper loss, which is a combination between L1 and L2 loss, which comes usually in value, depending on value to choose whether to use L1 loss or L2 loss. And actually we used like threshold link value as 1, since indirectly it speeds up the training process. Here's some experimental results. We compare like the proposed method room using the height exception as feature extractor and also context as feature extractor. We compared with the state of the art methods and room layout estimation, showing that our method can attain like the lowest pixel error in both L1 and video option, and while we are processing each frame at 102 milliseconds. Also for the modified exception, we can also obtain lower, like very small values, but it is not the best one, but it's also similar to the state of the art, like basic method. So, while like using the modified exception is much, the model is much lighter and can attain like better speed. Here are some like qualitative results obtained using the proposed method on L1 on the left here, and also Edo on the right here, showing that the proposed method can like predict very similar result to the ground truth here, showing like a very good accuracy of prediction of room layout estimation. Here we also performed some ablation study on the transformation layer. We tried to use affine transformation instead of the perspective transformation. Here we show the results here on the affine. In the case we use the affine transformation, it is obvious that the affine transformation is very limited. Since it can have very basic transformation to the network, and all the straight lines should, like parallel line should stay parallel. So that's why it cannot be used for this case, because the perspective transformation is the one required for this test, and also for sure it will be required. Also, we did some ablation study on the feature extractor. We tried different feature extractor instead of like the modified exception or the context time. Actually, many of them
you got stuck.
PG and this the things that it was using.
Hello? Hello?
Yeah.
You just got stuck a little bit. Okay. Are you still here?
Yeah. Still here, but I don't know. There's some problem.
Yeah, we missed your last slide, I guess.
Yeah. Can you hear me now?
Yeah. Okay.
Okay. So I guess like the last thing was like see about the aviation study on the feature perspective. So the limitation of this work actually, like in some cases, like there was some problem like in the extrapolation when the network try to zoom out of the scene. Sometimes they are using like just fading of the nearest value, which is untrue. But this happens like in some few cases when the network try to zoom in the scene and zoom out is the parameters, the learned parameters for the perspective transformation contain some zooming on or the zooming out like propose this problem like sometimes in some few cases we find like wrong extrapolation in the scene in these cases. But this will be like this actually doesn't affect like the accuracy.
We couldn't hear you.
We will give like some kind of we will provide some kind of like reference cubic for the 3D room, and also we use 3D spatial transformation to solve the problem of 3D room layout estimation. As a conclusion, the proposed method can efficiently learn the task of room layout estimation using the spatial transformation network. Also, the attained values for pixel error is 5.24 on LSUN and 7.1 on HITO, which is outperforming the state-of-the-art methods on LSUN and HITO. The proposed method also processes each frame in a very convenient speed, like 66 milliseconds in the case of using like the modified exception feature extractor. And that's all. Thank you for the attention.
Okay.
And,
yeah, thank you. I have a question, and for your reference, you have your reference layout in your network. And is it a must, or you can delete that reference layout?
yeah, I tried actually different references, and it was working. Like if we, it's the important thing is that all the sides should be appeared in the reference layout. And whatever the reference shape, the network also learned how to transform this reference layout to the required one.
Okay, and if you don't use it, if you don't have the reference layout, like say an arbitrary room that I never seen before, and would your network still work?
No, because like the network, actually this predicted layout is just a transformation of somehow like some reference layout. So reference layout is required for this.
Okay, case. Basically is a transformation matrix actually you are predicting. Right?
Yeah, right,
okay.
yeah.
Yeah, okay. Any other questions from audience? Okay, if no question, thank you very much.
Thank you.
Yeah, thank you. Actually, with this presentation, we end up our workshop. And today the workshop includes 7 speakers and 5 papers, and which comes from different perspectives and from real industry applications and from the research on the retraining models and training data to mathematics theories. And I would say that is very detailed and comprehensive workshop in this year. And if there is any questions, and for the audience, feel free to reach out to me or reach out to any of the speakers or paper presentation authors. And we are always glad to hear some feedback from the authors, and including the YouTube channel and for the future. for the future audience. And if you have anything, any feedback, feel free to reach out to us. Yeah, thank you again for all the people listening to our talk. Yeah, thank you.